Yeah, I guess I'm using they are really good. It's working. It might not be.
Does he sound like he's wearing a mic right now?
It doesn't sound like microphone.
It's muted. The light is back.
Okay. I feel like this.
About now?
But and actually, also.
About now?
Just up on Zoom.
I can hear it.
I'm glad you found them.
Okay, well, back our first speaker after lunch, Artur Izmaylov from the University of Toronto.
All right, thank you. Let me just start with thanking organizers for inviting me to sunny Minnesota. And today I'll be talking about chemistry and our efforts to use quantum computers to help chemists to figure out the solution to time-independent Schrödinger equation, right? So we've already seen this equation before. And the theme of my talk will be approximate symmetries, how they can help us to solve the time-independent Schrödinger equation on quantum computers, okay? And because majority, as like I'm guessing based on the program, majority of you are not chemists, I encourage you to raise hands if something is not clear. We had lovely discussion in the morning and would like to continue that. Right, so please don't hesitate to ask if something is not clear. All right, let's move on. So, of course, in early 2017, there were these old hopes that VQE can help us to solve Schrödinger equation, right, on the quantum computer. And many of you familiar with VQE. It uses quantum circuits to construct a wave function and then measures the expectation value of the Hamiltonian and does the feedback loop to lower the energy if we're after ground state, right? So now the hope was that with some help of error mitigation back then, we can solve some interesting problems. But we know now that we are really yet far from that goal, right? And the main issue really, besides all other problems with VQE, measurement, optimization, I would argue that the main issue is that we have circuit depth that kills all the advantage very quickly because the errors that accumulate, they're not corrected, all right? So the schematic plot of errors, cumulative error of solving your problem, my problem is Schrödinger equation, right? So eigenvalue problem. With the number of operations, I like to think like this, right? So you, in principle, if you're smart, choosing your operations, you construct more and more accurate wave function. Your error goes down, but eventually the error set of the hardware, because of the finite fidelity, they catch up, and we start losing all the accuracy we gain, right? And maybe it's your lucky day, and you are considering a small system, then desired accuracy could be spotted in this sweet spot, right? But in principle, in chemistry and in other disciplines as well, we are interested in scalable techniques, right? So we want larger and larger and larger molecules, and the curve will look like this, right? So this is not good, right? So because we cannot scale this up, and that's why we need to do something. So what do we do now? All right. So well, naturally, this symposium in general answers this probably question. We need to develop error correction to correct the errors, right? So, and that's indeed, I think, a long-term solid goal. But before this error correction, fully fledged error correction will be available, can we extract any usefulness out of the quantum computers, which are weak due to the circuit depth problems? And my answer to that is that we just need to introduce more flexibility to shift the load between the quantum and classical, right? So VQE already tried doing that, but it's limited in that flexibility of how much do you do on quantum and how much do you do on classical. And that limitation of flexibility comes from the simple fact that VQE has only one wave function. So one wave function, one circuit. So the system gets bigger or more complex, and then you run out of the circuit depth that you can allow, right? And that suggests a very natural solution to this problem. We need more wave functions, right? So how do we do that? we represent our wave function as linear combination, let's say, of small circuits, right? So these are our basis states now. We start with some product state, Hartree-Fock, very popular. And then we apply some unitary transformations of limited circuit depth. And we obtain the coefficients by diagonalizing classically on a classical computer the Hamiltonian matrix built in this basis states. Right? Very simple idea. It allows you to trade the circuit depth for the number of basis states. Right? So you could either introduce very long circuits and very few basis states, or very short circuits and more matrix elements you need to measure. Right? This is a natural gap or a breach, I would say, between the VQE, where we have only one state, one circuit, and what we know in the electronic structure, quantum chemistry, configuration interaction, where these states are just Slater determinants. You don't even need a circuit to build them, right? But you could be anywhere in between, all right, in principle. So this is you may recognize, some of you may recognize, this is a kind of a subspace expansion-like idea, which is not new, of course. Subspace expansion form was introduced back in 2017, right, by Jared McLean and others. And then there are several works, some of them listed here. And in all these works, essentially the formalism is, since we're using unitary transformations to construct our basis states, they generally are not orthogonal, right? And we end up with a generalized eigenvalue problem, which we need to solve. And even the original motivation for all this was a bit different, not to circuit depth reduction, but rather finding excited states, all right? So, and then there are some suggestions in some of these works that to take the unitary that is really produces their own like long circuits, right? So that's difficulty. And then there are a bunch of problems that you could think of with all these proposals. And well, there are a few here. So like one of the major ones is that the number of matrix elements that you need to measure that escalates very quickly. Then, because your unitary transformation produce non-orthogonal states, then you run into problems with condition numbers, linear dependency, and then you need to measure those matrix elements more and more accurately. Otherwise, you will get really big errors when you diagonalize some noisy matrices, right? And the circuit depth not always was good for these early proposals. That's why we decided that we want a subspace expansion method that has the following characteristics. We don't want to deal with non-orthogonal configurations, right? So we want to construct the unitaries that will give us orthogonal states. We would like to figure out how do we measure these matrix elements more efficiently, otherwise we'll choke on the measurement part. And then we would like to still have this flexibility of number of gates for the unitaries and number of matrix elements that we need to have. So we could, well, kind of with the advance of quantum computing, we may have longer circuits, or advance of the error correction, we have longer circuits, and then we will be able to get fewer matrix elements to measure, right? And then this optional part that ideally, we also would like to avoid optimization of our unitaries, because in principle, after solving the eigenvalue problem, we have these coefficients that compensate for some suboptimality of the basis functions in general, okay? So exploiting that could be an option. All right, so what do we do? It turns out that one of the key aspects of that can help us with all these constraints or all these conditions that we want to achieve is finding some approximate symmetries, or we call them sometimes quasi-symmetries. And so those are simple operators which are eigenoperators for the basis functions that we construct, okay? So it turns out that this simple relation helps us with the many aspects of this work. And they don't necessarily they're not chosen to be a native symmetries of the Hamiltonian, because that would be very restrictive. But they will commute with a large part of the Hamiltonian. So what they will give us, anyone who studied the quantum mechanics or even linear algebra know that if we get the states, eigenstates of the Hermitian operator for different eigenvalues, they are orthogonal by construction. right? So orthogonality will be there. And then the second important point is that because these symmetries, they will commute with some big part of the Hamiltonian, as we'll see, then only some part of the Hamiltonian that doesn't commute with these symmetries will couple the states of different symmetry sectors, right? So we will only need to measure this part. This part will be essentially producing a zero expectation value or zero matrix element because it commutes with symmetry. It doesn't couple the Bryan ket, which correspond to different symmetry sectors. Okay. So now the question also, how do we choose these symmetries? But before we get to that, let me tell you how the symmetries actually help us to reduce the circuit depth, because that was the very big problem originally. And I would like to illustrate a very simple point is that whenever you impose some symmetry constraint on your state, it's always going to reduce the entanglement. Okay, so here's a 2-qubit example, right? So we have a state, let's say a random state with coefficient, 4 coefficients for 2 qubits. And now we decide, okay, we want number of electrons to be respected by the state that we're constructing. And we use Jordan-Wigner transformation between fermions and qubits, right? So that's why, in a sense, the 00 correspond to no electrons, 0 and 110 correspond to 1 electron, and this one is 2 electrons, right? So if you impose the condition that this state needs to be an eigenstate of number of electrons, all of a sudden, these two are product states. This one is clearly has a less entanglement than the original one, right? So you reduce the entanglement by imposing the symmetries. And how do we impose symmetries in quantum computing? Well, then many of you familiar with this trick that if you use unitaries, then you can define generators, and all you need is these generators to commute with your symmetry operators. And if you then start with the product state that is an eigenstate of the symmetry, then you could use the generators that commute with the symmetry to create entangled superpositions, and they will be respecting the symmetry you want, right? So that's a usual trick. And the only problem is that, okay, so we have only just few kind of exact symmetries. And if we want to restrict entanglement so that we can fit the basis states into the circuits that we can allow now, then we need more symmetries, right? So, and we run out of the exact ones, so we create approximate. So what are these approximate symmetries? Chemistry helps us in this case. It suggests that maybe not a bad idea to use so-called seniorities. And for people who work on the error correction, you will see a lot of similarities with that concept. And the parity is checks that usually done to correct errors. Okay, so, and the idea is very simple. So if you have a, let's say, many-body system, you have these product states, later determinants for fermions, right? And then seniority is just counting the number of unpaired electrons, right? So every electron could be an orbital, which has alpha or beta spin, right? So, and then the zero seniority is all the later determinants with the paired electrons. Now, this seniority 2 is 2 unpaired, and so on, right? And on top of the total seniority, which counts the total number of unpaired electrons, we will be using mainly the orbital seniorities, this operator that counts the parity effectively of each orbital, right? So say this orbital is seniority 1, and this orbital is seniority 0, and the empty one is also seniority 0, okay? Now, with this quasi-symmetry, we can actually break down the Hamiltonian to 3 parts, and this, say, 0 part couples only states of the same seniority, 2 and 4 couples the seniority different, Bryan ket needs to be different by ±2 or ±4, all right? So that's the idea, which kind of helps us to do the measurement of matrix elements more efficiently. Now, why seniority is special in chemistry? So here's a primer in what chemistry actually is. It's studying the chemical reactions. That's what chemists like the most. So in chemical reaction is breaking bonds. So now this is the simplest model system, hydrogen. So we dissociate hydrogen. In the mean field description, we have a bonding orbital, fermionic mode, and antibonding. And when we dissociate hydrogen, the product state not anymore well described in the state of the dissociated hydrogen. It turns out you can write it down as two Slater determinants with the degeneracy of energies for the, well, now bonding and anti-bonding orbitals. And but you need a superposition of those, or entangled superposition of these two Slater determinants, essentially, right? And the nice thing about this construction is that you could see that only zero seniority is required. You don't need any other seniority sectors in order to describe the dissociation of hydrogen. And you need to believe me here, but you could check me after. But then you could break even single bonds with any single bond with the zero seniority sector. Okay. And then if you are more, well, kind of from the chemistry side, if you like to think about the dissociation of molecules and giving you some sort of unpaired electrons, or you've heard about that, and this picture sort of disagrees with that one, fear not, because we in principle can rotate this unpaired electron picture to the zero seniority picture by just orbital rotations. Okay, so it turns out that orbital rotations are enough to find the frame where the dissociation of single bonds is described just by zero seniority sector. Right? Now, when we go to the more bonds, because generally we would like to go to breaking more bonds, since it's a more challenging task, then it turns out that unitary rotations that come from the mean field unitary rotations, essentially orbital rotations, they are not enough to just rotate everything to the zero seniority sector. Okay, so we will need more sectors, but we can do that in principle. It's just to illustrate why zero seniority or seniority in general is a good idea in principle when you are describing the bond dissociation. That's the idea here. Okay, now in order for show that even with more bonds, we could be fine with the seniority as a ranking system for our states. Here's the example of nitrogen, and we consider electronic state, ground electronic state of nitrogen when we stretch the nitrogen-nitrogen bond, right? And so the lowest curve is the ground state with a full CI or exact answer. Hartree-Fock mean field description is right here, so it goes to the very high levels. High energies, so unrealistically high. But if we go zero seniority 0 plus 2, and up to 4, we already converge to the exact answer. Okay, so that shows that you don't need too many seniority sectors in order to describe multiple bonds. Yes.
I want to make sure I understand. This is looking at the authors. I assume that this is just a purely classical thing. Quantum.
No quantum. Yes. So it's a model system that can be solved on a classical computer. Yeah. Right. Okay. It's just to justify the use of seniority as a kind of not exact symmetries, but approximate symmetries that can help us to separate important contributions from less important contributions. Okay. All right. So now, how do we build our basis states? There are only two steps. We start with the product, as like in VQE in principle, we start with the product and we do these two steps. So the first step is, for quantum chemists in the room, is just essentially creating the configuration state functions. We unpair certain electrons from the Hartree-Fock contribution, and we unpair them, and that sets up a particular level of seniority, right? So. And they will not be changed, these places where we unpaired electrons, because the second step is just doing the pair rotations. So it takes the pairs and exchange them with the empty orbitals, and that introduces electron correlation, right? So these rotations, pair rotations, they don't move the unpaired parts. They're just, you could check the operator algebra. If you apply these rotations onto the configurations, so the singly occupied orbitals will stay in the same places. And so what we achieve with that is that W's could be used in a quantum computer by optimizing amplitudes, and they will preserve the seniority of the state. So seniority will be effectively set up by the first step, and then the W's will just introduce electron correlation that doesn't change the orbital seniorities anymore. Now, this construction also preserves the total molecular symmetries that we would like to keep, like a number of electrons and spin, right? And here, there is an interesting connection with the error correction codes with the construction that we just witnessed, right? So we have our states, essentially, they are all like this. They can be written as a linear combination of Slater determinants where there are parts where we have unpaired electrons and they stay there, but the paired ones keep moving because of the W's, right? And these orbital seniorities that we have, they are parities in the fermionic up to linear shift, the parity operators. And if you do Jordan-Wigner transformation for them, so you will see that orbital seniorities are just, again, linearly shifted products of Z's. Now, we have n orbital, 2n, n spin orbitals and n/2 orbitals. So that gives rise to essentially stabilizers in formalism, because there is always a Clifford transformation that will move these double Z's into products of into single Z's, right? And so the states after this Clifford transformation will be always presented as half of the qubits are in the product state and another half is an entangled state, okay? So 50-50 split because we've chosen that we have orbital seniorities as our symmetries for the state. And so then one can think of this as we have n/2 logical qubits that are in this encoding entanglement and n/2 syndrome qubits that entangle essentially the orbital seniority sector. And what's happening when we do these two transformations, V and W, the V is essentially introducing the syndrome, and the W introduces, it's like a logical operation because it operates on the logical qubits. It introduces entanglement in the entangled sector, okay? So that's the connection with error correction codes. And it also helps us to do the measurement more efficiently. After that separation of the state into two parts, one is purely product part and another is entangled, we can put this transformation on our Hamiltonian, which is a linear combination of Pauli products. And then each Pauli product could be split essentially on the classical and quantum parts. And we can integrate the classical part because it corresponds to this product part of our state, right? So we could do this integration on the classical computer, which creates the effective Hamiltonians that then we need to effectively measure on a quantum computer, but only for the half of the qubits that we have, right? So that measurement becomes, much more efficient because a lot of terms essentially disappear or get canceled. So we're very happy with that separation to reduce the number of measurements. And here are some results of this, what we call QSense, quantum seniority-based subspace expansion. More details in this archive reference, right? So here we have the nitrogen problem. It's a kind of simulator results on the classical computer, but we're planning currently to move it on a quantum computer. So this is an error in millihartries. The gray line is the chemical accuracy. We want to be below it. Right, so this is a bond dissociation, and these two methods are typical classical methods that people use, and they are polynomial in scaling, and they both kind of break down in this challenging problem. Okay, now QSense, there are two versions. They differ depending on whether we optimize the amplitudes more or less. I'm not going to go into the details of that, but the good news is that they go below the chemical accuracy line. And then if we look at the number of measurements, let's say for building the entire matrix of the Hamiltonian, we need about 3 to 5 millions of measurements, which is twice better than the VQE case for the final cycle of the VQE with the final state. We only need from 100 to 200 C-nodes, so it's kind of becoming closer to what is available, but we could probably reduce it even further by introducing more matrix elements if we want. And the dimensionality of the matrix is also scales between dozens and hundreds. Okay, yeah.
So again, the data is a classical
Classical
simulation?
simulator, right?
Okay.
Yeah. Okay, so that's the performance, and
Maybe I can ask when we're on
Yeah.
this slide. Can you maybe re-explain to me where the sort of quantum advantage
Mhm.
might come from? So it's motivated with a lot of symmetries, which were used classically
Right.
to generate CI-like expansions. So that's a very classical thing.
right.
And so the quantum part,
The
like
quantum part is this pair rotations, right? So because this part, in principle, CSFs that we create, they can be created on classically, people have done it, but this part requires quantum in general. And that this is the part in this representation where we split the entangled part from the non-entangled part. The W's essentially create the entanglement, right? Because whatever V part is doing, it could be essentially rotated into the like product state.
What do you do with this wave function? Maybe that's what I missed. What is once the quantum computer created this wave function?
We create matrix elements. It's like a variation, a linear variation of
Matrix element.
matrix elements of the Hamiltonian and diagonalized on a classical computer. Yeah. So essentially, your basis functions could be as quantum as you want, or as quantum as quantum computers that you have would allow you, because the circuit depth is not infinite, right?
Okay, but if these matrix elements are, if we talk about scaling, so suppose the system is big, how do these matrix elements scale with system size?
Number of matrix elements, like here we
the
have
size of the matrix elements.
Okay, so here's where we have a flexibility. In principle, if you allow yourself complex functions, which will require longer circuits, then it could end up with being just a VQE, which is a one matrix element, right? But if you cannot allow long circuits, your basis functions will be small in the circuit depth, right? And then you will need a lot of them in order to build up to the complex wave function.
And my problem is that I don't have a problem with the diagonal matrix elements. They're probably big, as big as that. But off-diagonal matrix elements could generally be exponentially small in system size.
Yeah, sure. Could be zero.
And then capturing them would be exponentially hard. Like you need to measure the sample complexity in order to capture exponentially small matrix elements would grow exponentially.
Well, we have a ways to figure out that like what part of the Hamiltonian do we need to measure for them, right? So it's not the entire Hamiltonian, it's some part of it. And then we could even screen that. So those are, and again, depending on number of matrix elements, if there are just a few of them, then we could and if they are small, we could sample them and see what the results will be. So like it's the same problem as a VQE.
Yeah,
measurement.
VQE, VQE has the same problem, but it means that there is some exponential complexity even in this quantum algorithm to get relative errors, not additive errors. Because I mean, sure, if you just are willing to approximate it using only diagonal matrix elements, that's fine. But then I think
we should probably talk more after, because I don't see the difference between diagonal and non-diagonal. Actually, diagonal cause more troubles because they're bigger.
For the sake of time, can you hang on?
Let's
let them finish. More questions at the end, and then copy.
Yeah. Okay. So of course, we understand that orbital seniorities may not be the ultimate solution for all the systems. Let's say some of the complexity in chemistry comes from transition metal compounds, for example, right? And there, the chemists intuitively already know that, well, there are d orbitals, they are localized, so that probably good quasi-symmetries will be related to number of d orbital electrons or local spins. And so we have all that in mind and have the plans for essentially finding these system-dependent approximate symmetries through algebraic search, where we look for local, mutually commuting, and functionally independent symmetries in this form, where we conjugate with orbital rotation some local polynomials of occupation numbers. All right, and that could be the orbital rotations and these polynomial functions of occupations could be optimized based on some host functions that involve, as you could imagine, commutativity with the Hamiltonian and some information about the state, like some symmetries could be better for the ground state and some for the excited states, right? So we're already looking using various host functions, and we already found that when we stretch a single bonds through this brute force sort of search, we are finding orbital seniorities being pretty good approximate symmetries for that case, which is reassuring. So we would like to move on into the more difficult systems and find these approximate symmetries, which will help us to partition Hilbert space there as well. Okay. With this, how much time do I have?
A minute or two.
Okay, so then I'll skip the other part, which is using approximate symmetries for improving the block encoding and fault-tolerant algorithms. This is truly maybe more aligned with the topic that it's a horizon of quantum chemistry on a quantum computer, right? Because we would like to go to the fault-tolerant algorithms, and believe me when I say that in principle you could create more effective Hamiltonians, more efficient effective Hamiltonians using approximate symmetries by integrating out some degrees of freedom effectively. Right, so I'll skip the details here, and I would like to just summarize that by imposing this approximate symmetries relevant to the physics of the problem, we reduce quantum circuit load and put more load on the diagonalization problem in a classical computer. And so to reduce for the entanglement, essentially, we have these matrix elements that we diagonalize. Approximate symmetries could be also used in the fault-tolerant architecture algorithms. And with that, we could also go to the excited state on non-Hermitian Hamiltonian problems, because when it comes to the diagonalization, you in principle can treat non-Hermitian Hamiltonians, and VQE, for example, doesn't have a capacity to do that. And last but the most important slide, people who did the work, and my collaborator from York University, Toby Zhang, and these companies and for support and funding, and all of you for your kind attention. Thank you.
I think I'm lacking intuition about the appearance of this air correcting call that showed up. Is it fully determined by the Hamiltonian being simulated? Is it always?
It has nothing to do with Hamiltonian.
The system being simulated. Is it always weight 2? Is it always rate 1/2? Where does what imposes what that code is?
What imposes what that code is the symmetries that we make our states to be eigen operators for the states, right? So we first choose operators, set of operators, and we say we want states that will be eigenstates of those operators.
And is there value to, or is it a meaningful approach to start with a code that has some properties and then from it deduce?
Yes, because that's where probably Hamiltonian comes in, because if you want to address a particular many-body system, it has a Hamiltonian knows everything, right? So then you are trying to build simple operators that are almost commuting the Hamiltonian, right? So then using eigenstates of those simple operators, you probably won't need too many of them, right? So that's what the intuition. And then it so happened that these orbital seniorities as the symmetries that we impose, they are, because they are products of these essentially, they could be connected with stabilizers in the qubit representation, right? And stabilizer states. Yeah.
Gotta be a quick one.
Yeah, let me try to, because this is a problem that maybe you'll be able to explain that I never understood from this chemistry talks. If you only take, if you only use diagonal matrix elements, then it's just a variational approach, right? Basically, you choose the one that's smallest and that's it. What you want is a good basis to kind of solve a matrix equation. The problem is that off-diagonal matrix element, if you really want to talk about quantum advantage, you want to scale to the large system limit, the off-diagonal matrix element generically will have an exponentially small value because it's
Why can't they be compact and sort of a small number of them? Yeah, so not
because of orthogonality catastrophe. So then if you leave them alone, then okay, that's fine. But then you're back to the same variational approximation if you want to ignore them. If you don't ignore them, then you're still again with.
No, we're not ignoring any of diagonal elements. I agree that it may eventually be the case that you need a lot of measurements to measure all of them.
Exponentially large number.
Exponentially large systems will lead to the exponential complexity in general, right? So
yeah. So then there is no, in this sense, there is no quantum advantage in using quantum computers to, but maybe there is.
Okay. I think maybe one thing to say, simple thing to say, is that 2 electron Hamiltonians, by varying the parameters, you can always make a QMA complete problem where VQE has no chance and QP doesn't have a chance. Right, so that's was shown, right? So we think that the nature is not playing against us, and so the systems that we are studying, we could do in polynomial number of generators, and experiments show that that's the case with VQE at least.
Polynomial number of generators, but not polynomially large number of samples. In the end, you want to put it in the quantum computer and measure some expectation, some matrix element, and to get that value will take many measurements.
Right, but not exponentially. Yeah.
Coffee chat.
Okay.
We got to move to our next speaker. Let's thank Artur again. Okay. For our next Bryan Clark from the University of Illinois, Urbana-Champaign. Let's see how easy the setup is. Then Bryan, I've got hard results last time.
Good. What are the hard times?
15, 10, 5, and stop.
Awesome.
Put that on, maybe on your pillow would be a good spot. And then I think it's muted right now because the button's red, but if you press it, you might unmute. And then this, are you HDMI or USB-C?
USB-C.
Give it a minute. Just thinking about its own choices.
Wow. There's an open, maybe even so.
Let's see if this is what is this hooked up to. We can't do that. No, because you just disconnected.
Did I invert it?
Everything's
sorry.
broken. You can use this one to if you need to. Or you have a USB-C direct.
And that's okay.
Not in the thermodynamic link, not when you take the large system limit. And especially his way of generating different states.
I think about a chain and I will just.
Okay.
More in the this matrix of
Say if you in your
Think that's on?
basis,
Really?
because you're constructing matrix.
So like, look at the work of chain will produce, right? Some of these.
Yeah.
It'll be this.
Okay, again, we've got Mark next by C.
Great, thanks everybody. So I'm going to tell you sort of about parts of the quantum classical divide. So this will be a little bit of Matt's talk and a little bit of Leon Fu's talk, a little bit of some other things. Let me actually start by talking about none of those things. So it's always good to start talking about the thing you're not going to talk about in your talk. So my research group works in the area of quantum computing and computational condensed matter. And so some of the things that we work on that I won't tell you about, we're doing a bunch of quantum error correction work at the moment, using neural decoding to decode quantum LDVC codes with diffusion models. We're working very closely with superconducting qubit experimentalists, Wolfgang and Angela, for example, developing new proposals for composite qubits that should have much better dephasing of bit flip errors. We do a bunch of machine learning for experiment, working with Finchain Wang's group, taking her 40 stem microscopy data and turning it into atomic locations. And we do a bunch of random quantum circuit work. I want to tell you about none of that today. I want to instead tell you two stories. about the quantum classical divide, sort of trying to understand both practically and sort of fundamentally what is the difference between what can be done classically and what can be done on a quantum computer. And I like this for two reasons. I think it's both practically important, right? We'd all really like to answer the question, what are we going to eventually do on a quantum computer? Will we really win against classical devices? And one of the stories I'll tell you is in the spirit of a lot of what we've been talking about today, which is how do we push forward quantum computing algorithms, and how does that compare against various classical algorithms, all in the context of simulating physical systems. The other thing is I think this is a deeply fundamental question. I really think sort of answering the question, somehow where does the power of quantum computing come from, is very interesting. And if I get to it, I'm going to tell you a story where I say, look, we can't simulate all classical circuits efficiently, but we can simulate some classical circuits efficiently. We've developed an algorithm that expands that class significantly. And I think that has something interesting to say about sort of this divide between classical and quantum computers. I should say the border might be porous, right? There might be lots of quantum classical hybrids. Almost certainly, we're going to need to use a lot of classical power for error detection and error correction, but it may also be that there's lots of algorithms where that's useful. Okay, so I'm going to start with my first story, simulating physical systems. And there, notice we have the scale, and the scale is very smartly chosen. I don't know, come to my pointer, there we go. With classical winning significantly above quantum. That's certainly where we are today. And I think it's still an open question when and where that's going to change. Okay, so I'm going to first tell you about, well, a very biased view, but sort of a lot of our work in trying to push forward quantum computing algorithms for simulating quantum physics, and then say a couple words about classical algorithms we've developed for simulating quantum physics, and then go off to story 2. Okay, so look, what is the situation? Well, essentially the situation is really, there are lots of quote unquote exact algorithms, qubitization, quantum phase estimation, SQD, kind of Krylov subspace things, and they all require you to get, to start these algorithms relatively close. Essentially, the cost of all of these things depend on 1 over the overlap, where that overlap is dependent on what it is you want to get down to. So if you want the exact ground state, your 1 over overlap has to be pretty good. And what is the good news? Well, the good news is probably it is the case for most quantum circuits that, for most states that we care about, that the quantum circuits that we need are relatively shallow. Maybe log, maybe linear. Here's an example. This is transverse field Ising model data, and we're just asking, look, we just optimize 1 layer, 2 layers, et cetera. How quick does it approach the ground state? It approaches it extremely quickly. But in general, right, the typical quantum circuit, the typical state requires an exponentially deep circuit, but that's probably not where most of nature is. And in fact, we've been doing a bunch of work with measurement plus adaptive feedback. That's where instead of having your quantum circuit be unitary, you say, well, my quantum circuit is unitary for a while, I do some measurements, and then I turn classically on those measurements and conditioned on those measurements. I have a new and improved quantum circuit for the rest of the circuit. And if you do that, you actually can even decrease the circuit depth even further. So we were able to show this analytically for a class of states. This was first noticed by this group, including Nathan, who is not quite here yet. But we were able to develop an algorithm where you say, oh, please find me a state that generates this for transverse field Ising model critical states or subset states or random MPS. And what we find is every time we ask it this question, if you're willing to use measurement plus adaptive feedback and you fix the depth that your circuit runs to, the state that you get out can often be an order of magnitude better. So here, this is on a log scale, the infidelity. This is jumping from same depth with unitary plus adaptive feedback, unitary plus adaptive feedback. You gain order of magnitude there. In subset states, you gain like 10 orders of magnitude because subset states are really hard to build, but easy to do with measurement plus adaptive feedback. If you don't know what a substate is, it's like the sum of 3 binary numbers or something. So these are important in quantum cryptography and things. Yes, Fiona.
Sorry, are these all like, I have a Hamiltonian and I'm trying to find the ground state?
No, these are all, and my goal is to state prepare. I have these particular states that I want to start with, and it takes me either a certain unitary depth to do it, or unitary measure conditioned on that measurement more unitary. And the state preparation is just an order of magnitude better using this alternative approach. And we have a classical algorithm that often finds it. Great, thanks. Other questions?
Yeah, do these adaptive protocols prepare mixed states in general, or are you talking about adaptive?
Yeah, so that's a really good question. They could prepare mixed states, but we looked, and during the optimization of our techniques, almost instantaneously, they find a pure state and they stay there forever. So for reasons we don't deeply understand, although they could prepare mixed states, that's never what they do.
And I should think of these as you're measuring 1 or 2 qubits nearby, and you're allowed to perform any non-local classical process. 1
or 2 qubits nearby, allowed to do any non-local classical computation. And I should say, like, we first tried to do this with stochastic gradient descent, and it was a disaster. This requires a huge amount of like tensor network, environment tensor, like tricks to pull off. But you throw those things at it, and it seems to work pretty well. It's a question about how well we can scale, but for reasonably sized systems, we do well. Great, other questions? Okay, so that's the good news. The circuits we need might not be too deep, and we might be able to make them shallower. But nonetheless, it's hard to get there. And many sort of variational algorithms, they're a little bit out of favor at the moment, although I think they're still going to be an important component of our eventual approaches, converge slowly. So here, this is doing stochastic gradient descent for some, I don't know, 7 qubits or something, or 14 qubits, and we need 10 to the 6 expectation measurements to get our fidelity kind of 90% up there. They have barren plateaus. What a barren plateau is that the energy landscape is extremely flat. And so if you have noise in your gradient, you're just as likely to go uphill and downhill. So this is the decrease in energy you get. And if you have a little bit noise on your stochastic gradient descent, lots of times you actually walk uphill, which is a little unfortunate. And they often get stuck in local minima. So here are particular examples. These are all emulated on devices. Okay, that's all well and good. So what is sort of the path forward in terms of algorithms on quantum computers? Well, the game is you have to start close, right? Because if you're going to sort of follow up with quantum phase estimation or qubitization or whatnot, so how are you going to start close? Well, the best thing you can do is if you can get away with figuring out how to initialize things classically, how to just like churn on your classical computer and find a good state, well, that's ideal. And so we've done some work, at least preparing states in interesting phases. So we can prepare projected mean fields on quantum circuits, on quantum computers relatively efficiently. And so that at least gets you into various spin liquid phases, if spin liquids are your thing. The other thing is we've done some work where we said, well, we can't actually run a quantum computer. Suppose we emulate it very poorly. Is that good enough to at least start us in a reasonable place? And it is. It starts you in a much better place than throwing random parameters at your circuit. So that's good. And then once you're there, you need to ask yourself the question, well, what am I going to do at this point? And so one option at this point is, okay, you're really just going to have to like up your game in terms of some sort of variational approach. So we've worked very hard on taking variational optimization, where people have historically done stochastic gradient descent and done much better approaches, things that look a lot more like DMRG, you sweep over gates, or linear method in variational Monte Carlo. We've done variational measuring time evolution. And if you play these games, you can often decrease the amount of measurements and expectation values you need by 1 to 2 orders of magnitude. So that's good, although it's not clear that that's good enough to solve our problem, because we need an insane number of measurements to get where we want to go. The other game you can try to play is you can say, well, the thing that works really well on classical computers in many cases is tensor networks. Maybe we can sort of port tensor networks onto quantum computers. Why in the world would you do that? It already works well classically. Well, one motivation is that the bond dimension you get access to is exponential in depth. And so an exponential bond dimension is great. Now, I have that in quotes for a good reason, because you don't get access to the full exponential set of bond dimension. Just by parameter counting, you know that's not possible. But it is true you get access to some of the exponential bond dimension space. So I can take a tensor network, I can promote all the tensors to unitaries, I can get access to that exponential bond dimension space. And so now what you're hoping is that the things in that exponential, the quantum states in that exponential bond dimension space are relevant. And there's some reason to believe from papers of Garnet and otherwise that that might be the case. But there are a huge number of like practical obstacles here. So for example, there are barren plateau problems all over the place. There are barren plateau problems with the number of sites. There are barren plateau problems with the bond dimension. And so you just have to do like a lot of technical work to like get your optimization to do anything sane in this situation. So essentially, we've done at least some of that work to fight the barren plateau problem with respect to sites. You can do things where you sort of train early sites in this matrix product state first that moves you into a better spot of the energy landscape. And so the later sites are trained much more efficiently to deal with the barren plateau problem with expected bond dimensions. You can start in a small bond dimension and ramp up. That's what's done classically anyway. But actually, that's a little bit tricky because the unitary circuit for the small bond dimension and the unitary circuit for the large bond dimension look qualitatively different. So you have to play some like funny games where you figure out how do I take a chi=4 bond dimension quantum circuit, turn it into a chi=8 bond dimension quantum circuit. You can do that by adding a bunch of swap gates and identities and then going back and optimizing these. All of this is technical, right? I'm not going through all the technical details. What I'm telling you is that if one fights with enough of these technical details, one can often get the optimization to be somewhat sane, even in the face of these barren plateaus. Okay, these are some pictures. Here's again all emulated stuff, but on say 24-site transversal lysing models, we can get our fidelity sort of non-trivially lower than 10%, running some of these emulated things. If we use fancy barren plateau resistant things, we move from this energy curve, which is plateauing kind of high, to this energy curve, which does much better, et cetera, et cetera. Okay, fine. You finally get around to like, actually, let me say something else. This is one path forward, trying to push something variationally. The advantage there is you're finding kind of a good circuit. The disadvantage is that really you have to push a lot of shots. So you're going to optimize and do shots over and over. This is why this has fallen out of favor a little bit. The trade-off is you do something like adiabatic state preparation. We haven't thought very hard about this at the moment, but this trade-off is that you're going to have to do a lot of depth. Right? To adiabatically state prepare, you start kind of in the right phase. Maybe you want to start in a spin liquid phase, and then you adiabatically move yourself to the state that you really care about. That's going to be okay, but now you've got to run a long Hamiltonian dynamic for each and every time you do it, even when you want to go ahead and measure it. Okay, and then once you start close, what you do, well, now you apply the standard things. Well, actually, you hope that your tensor network or variational thing was good enough to start with, but often it's not. And then you do qubitization or quantum phase estimation or something. I mean, even there, you want to worry a little bit. I mean, these are generic algorithms, which is great, but both a feature and a bug. What it means for it to be generic is that, in some sense, kind of the efficacy of this is somehow bounded by the worst Hamiltonians. And so this is not the problem we'd really have liked to solve, but we have at least started thinking about the problem. Can we modify, say, qubitization for non-generic Hamiltonians? If I promise you some properties of your Hamiltonian that is special in some ways, can you do something that allows you to do better? So here we managed to solve the following problem. If I promise you that you have a nearly frustration-free Hamiltonian, we can modify qubitization in a way that actually you get better parameters than you can generically. Okay, and so that's nice, although not many of you have nearly frustration-free Hamiltonians you want to work with. We try to do this first for like stochastic Hamiltonians and other things, and we failed.
What do you mean by nearly?
So you know what a frustration-free Hamiltonian, everything commutes, and nearly essentially means that the ground state energy is like not too far away from it. We have sort of a formal definition as you turn off the nearly, like it goes from something that's good to something that.
Should I think of it as a frustration-free Hamiltonian with some small but extensive perturbation?
Yeah. Okay. And then the one thing that I don't think have talked very much yet today, but actually is really important, is that you really want to then use whatever you're getting out of your quantum computer in a fruitful way. So all of this process that we've talked about, well, the variational maybe you only need to do once, but then you need to get some sort of result out. So a lot of people like to say the words, write in those grant proposals, oh, one day we'll solve pharmaceuticals or something, or do various reaction components. What do we mean by that? Well, roughly we mean we have a potential energy surface of some molecule. And so we've spent some time thinking about, can we use classical machine learning to learn potential energy surfaces from the output of quantum computer in an efficacious way? And people have done this for things other than quantum computers, but you can say, oh, the quantum computers are particularly expensive. What are all the tricks that we can sort of put together so that we can fit something well? Or can we take the quantum computer output and train a generative model on it so you can get the results out of that relatively approximate results back even from a classical place. Or lots of people have done classical shadows. We sort of pioneered a device or channel version of classical shadows. You scramble, run your unitary scramble, and then in expectation, you have the information you need to run your quantum computer again on your classical computer. Now, the variance can be high depending on what your inputs and outputs are going to be, but all of these are in the spirit of trying to fruitfully use your output. Okay, questions so far? Okay, so I'm going to just move on for a minute and say, look, the classical, those were sort of our attempts at pushing the quantum computing algorithms. The classical algorithms for these things are just much, much better than most people sort of appreciate. So I'm going to tell you one about we've developed. This is my favorite one. So look, we have a wave function, the neural backflow wave function that is extremely powerful. It is generalized in many, many different ways, Fermi-net, Poly-net, various things. Lots of people know about Fermi-net because Google's PR is much better than mine. But what this technique does is the following. It eats configurations, and those configurations are used to generate a set of single particle orbitals. And then those single particle orbitals make up a Slater determinant. And so what this is a configuration-dependent set of single particle orbitals where the single particle orbitals are generated by machine learning instruments. So Liang Fu talked about something related to this earlier. And we really think of this as sort of the best thing at the moment for 2D periodic fermionic Hamilton.
Sorry, when you say configuration dependent, what is that? What kinds of configuration?
So let's say you have the locations of your electrons. It's encoded as a binary number, but not important. We're on a lattice with the locations of the electrons.
Like in a ground state, or like
no, like
or
up, down, down, up, up.
You're trying to do dynamics.
No, sorry. This is a variational wave function. It eats a configuration. It eats where the electrons are and spits out a number. And so it's going to eat where the electrons are at any given instantaneous like sample. And it's going to spit out the number by generating a special set of single particle orbitals that is dependent on this choice of where your electrons are. Imagine you have 3 electron sites, double occupied, spin up, spin down. With that particular configuration, it will have a bespoke special choice of single particle orbitals that come from some machine learning architecture. And then you would pretend those are single particle orbitals for this configuration and evaluate it like it was a Slater determinant.
It's determined, not Slater determinant. Yeah, just to clarify that.
Think of it as a instantaneous Slater determinant.
And the idea is you want to compute the energy of this
The idea is this is just going to give you the amplitude for this particular configuration. And then you can use variational Monte Carlo to compute it. So let me just step back a moment.
Okay,
so
but the amplitude for this configuration in a ground state of the
this is a attempted optimized ground state.
Okay.
Sorry. Is that clear, or should I other questions about what we do?
Yeah. Okay.
So, yes.
Is it guaranteed to be normalized? Or
it's in variational Monte Carlo, so yes. It's a variational Monte Carlo, everything is automatically normalized. This is not guaranteed to be normalized, but because we're computing the energy and all the other observables in variational Monte Carlo, it is normalized. Any questions?
If you choose the orbitals to build the sort of Slater determinant in a way that depends on the configuration of all of the fermions, how do you ensure that you have anti-symmetry?
Because we're in second quantized on a lattice and the anti-symmetry happens no matter what.
Oh, I see. Okay, just built in.
It's essentially a basis of Slater determinants.
Yeah, the trouble would have been that I would have imagined that if you change the trouble, right.
Yeah, okay. You could write down something that's very, very bad, but still anti-symmetric. And you're optimizing the heck out of this with a million parameters. And so it turns out not to ever be very, very good. Yes.
Just I'm sure you agree with this, like in the target problem is a n-particle antisymmetric function. That's a ground state. And in this approach, each orbital in the determinant is already a many particle wave function. Is that correct?
In the second quantized approach where we are, each configuration is already a second quantized.
But it doesn't matter whether it's the second or first quantized. The important thing that each orbital in the determinant, in your case, is already a configuration dependent, meaning that's already a many-body state.
Yeah, that's true. But it's also true that at least in the lattice, there's no way to write down something that's not anti-symmetric.
I agree that the anti-symmetry is preserved. I'm just saying in terms of complexity, eventually we want only a single m particle wave function.
Yeah, it is a single m particle wave
And
function.
here you basically have n m particle wave function because each orbital in the determinant is already a fully many-body wave function. We can talk more
Each
later.
orbital depends on all the electrons.
Yeah.
That's correct. Any other questions? Okay, and we can just ask how good this is, and it's really, really good. So we do a bunch of molecules, and we essentially get the exact answer. We run things on hydrogen chain benchmarks. There's a Sinha benchmark, and we beat all the other approaches. We get the nitrogen dissociation curve really well. We compare against various IBM things, and I don't know, they extrapolate to like 10 to the -1 away, and we're extrapolated to the exact answer, and our variational energies are 10 to the -4 away. We beat all the published trim CI results for the relevant molecules, although the new 2-hour talk trim CI results are still the jury's out on. We do really, really well on molecules. We also really, really do well on lattices. People like to go, the quantum computers are going to solve the Hubbard model. What do we mean by that? We mean we're going to stick like 64 qubits or 100 qubits or something on a quantum computer, and we're going to turn on T prime, and we're going to measure like a superconducting order parameter. We already can do that like super, super well. So this is like a 4x8 and a 4x16 T prime of 0. And those energies are like relative energies of 10 to the -4 and 10 to the -3. And we get like beautiful Hubbard stripes. And you can go ahead and turn on a T prime. You see a very beautiful, like saturating superconducting order parameter that's sort of at the order of like, I don't know, 0.14 or something. And all of this works beautifully. And this is all highly accurate. And so if your question is like, does the Hubbard model superconduct? I don't know. You should probably do lots of finite size systems and extrapolate. But like, does this have a non-trivial like order parameter at 8x8? Yeah, this system size it does. Yes.
Can you talk a little bit about scalability to larger systems?
Yeah, so the algorithm itself goes sort of as n to the 4, n to the 5, depending on how you're doing. So it's a bit slow. This is sort of our biggest bottleneck, particularly because it's running on GPU. So things get slow fast. And then in terms of accuracy, well, that's an empirical thing, but we seem to preserve a lot of accuracy, although like as we went from 32 to 64, like we lost kind of an order of magnitude. So I think our scalability is quite good, but it's also like a little polynomial, but also a little bit slow. And so that's in some sense the biggest bottleneck, and we're working on it. Generally, we compare against DMRG, like open boundary condition things, and we compete favorably at sort of DMRG of 4,000 or 6,000 on places where DMRG should be good. I don't know, at 20,000, we kind of start using periodic boundary conditions. Questions about that? Okay, so I think the upshot of this is the classical algorithms are just really, really good. And like, we don't think this is our limit. We are getting better. And this really has sort of transformed sort of the solution of like 2D periodic formulas. Questions before I move on to story 2? How many minutes do I have left?
About 5 minutes.
Great, more than enough for story 2, at least to tell you the results. Okay, story 2 is totally different, but also on sort of the border between classical and quantum computation. An interesting question is like, what circuits can you simulate efficiently possibly? Right? Okay, we all know, or many of us know, that Clifford circuits you can simulate efficiently possibly. So what are Clifford circuits? Clifford circuits are circuits made up of Clifford gates. And then if you want to do universal quantum computation, then you can just supplement it with a bunch of T gates. And so I think an interesting question is the following. You know, 0 T gates are actually log n T gates. You can just do with standard stabilizer techniques. And poly n T gates is universal, so you certainly can't do that. We know that in general, quantum computing should be better than classical computing. And so now there's like a big gap between log n and n. So can we kind of close that gap? And I'm going to cheat here and say what I mean by simulate is compute a poly expectation values with respect to these. Those of you who like sampling can ignore the rest of this 5 minutes. Okay, and our answer, which is about as far as I'll get, because I'm going to tell you a detailed version of our answer, is that there are many, and I'll give you an algebraic characterization of that in a moment, many Clifford circuits, Clifford plus T circuits with n T gates, which can be simulated classically efficiently. Okay. And so here is a actually algebraic characterization of which one of those circuits they are. Here is a Clifford circuit where I've added in some random T gates. And what T gate is alpha I plus beta B, cosine pi over 8 I plus whatever, sine pi over 8 C. And so I can commute my T gates out of my circuit. It's commuted out of the circuit, I get alpha I plus beta P, where P is some multi-qubit polystring, DXLI XXX or something. And then if I just took this, I could just like collapse this all in and I would get an exponentially large MPS, which is no good. And what I'm going to show you is here's my statement. Let us just write out this table of polystrings, ignore the alpha I plus beta P for a moment, and then do a mapping to a GF2 matrix. XY goes to 1, IZ goes to 0. This is a GF2 matrix. There are null vectors in this GF2 matrix. And the statement is the cost to simulate this circuit is exponential in the number of null vectors of that matrix, plus order n cubed for Stevens or stuff. Period, full stop. Okay, so that is the algebraic characterization of what you can do. How much time do I have left? 3 minutes. Good. Let me tell you the algorithm. So here's the game. What I'm going to do is I'm going to pull T gates out one at a time. When I pull the first T gate out, I have something like this. What I'm going to do is I'm going to consume one of my qubits, one of my zeros, so that I'm left with a product state. What I'm going to do is I'm going to consume one of my zeros, and then I'm going to add onto my circuit d dagger d. The secret of all physics is to multiply appropriately by 1. Here I'm going to add d dagger d, where d and d dagger are both Clifford circuits. They're control polys. And so what I do is I take a place where x attacks 0, x is hitting a 0. I add this Clifford circuit. What that does is that cancels out the rest of that polystring. Okay, and so where I'm left after this is my D gets absorbed here. It sort of consumed this qubit. It's now still a product state with some other qubit. And now I have a D dagger attached to my previous C, but that's okay. My invariant was I just had some like Clifford plus T gates in it. Now I just have a bigger Clifford plus T gates in it. And then I just do this over and over again. Pull the next T gate out, find a thing, consume it, make my Clifford bigger. Occasionally what will happen is that I have no X and Y hitting a 0. If I have no X and Y hitting a 0, I declare failure. What happens when I declare failure? Well, I entangle the qubits that I burned, but I don't consume or touch any of the other resources that I have. Okay, and so this is very nice. What that means is this is going to be exponential in the number of times that I failed. But as long as I have something where I didn't fail, then I've just like left the state with exactly the same amount of entanglement that I did before, possibly a bigger Clifford. Okay, and what does this mean? Well, this means in practice that as long as you have deepish T gates, you're in good shape. You have deep T gates, the light cone is large. You essentially, for all intents and purposes, have a random polystring. And the rank of this set of polystrings is going to be essentially full. There just aren't going to be very many null vectors. If I have shallow T gates, I have a bunch of identities here. This corresponds to a bunch of zeros in my GF2 matrix. And then, well, I'm going to have a lot of null vectors, and this is a problem. You could do some fancy numerics and convince yourself that really what I want my T gates to be sort of uniformly spread out and at least log down. Maybe log squared out. If you're in a situation like that, then roughly you can absorb n T gates. Anything more than n, and then you begin pulling up rank, right? If I have a matrix of size 32, and I have like 50 columns on it, then my rank is at least 50 times 32. Okay, what I haven't told you, and I'm not going to tell you because it says stop there, is how the number of failures is connected to this algebraic characterization of null eigenvectors, but I'm happy to tell you in person if you want to know that. So we'll jump to the conclusion, and my second picture of my group, who again are the people doing all the work. Thanks.
Okay, we have time for a few questions.
So about the quantum circuit simulation,
Yeah.
as you mentioned, you are circulating the observables,
We are only able to calculate poly expectation values.
right? Just on curious, like have people tried like simulating the quantum state themselves?
I mean, we have a representation of the quantum state as a Clifford circuit times a small MPS, but then we don't know how to write that in any better way.
Can I ask a second question very quickly? Yeah, about the neural wave function part. Have you tried doing a diffusion Monte on top of the?
Yeah, we have.
And how does it?
It improves things, but it doesn't improve things infinitely. So we have a whole paper. We did diffusion Monte Carlo and Lancho steps and sums over symmetry sectors and various other things like that. All of those improved things. The sums over symmetry sector sort of did the best. I'll show you the paper. We can talk offline about it.
This could be like some sense be a benchmark of the accuracy of the neural wave function itself.
The diffusion Monte Carlo result?
Yeah, for the point, my point is that like if the energy still get further lowered a lot, right?
Yeah, I should say there's a better, yes, but there is a better thing to look at. We've done variance extrapolation, which is extremely clean. And for most of these things, if you're like, do you know what the actual ground state energy is? Like you have a very, very good extrapolated estimate.
Sounds good. Thanks.
Your neural backflow are really good. DMRG is sometimes really good. I say TrimCI is somehow really good. These seem to be three totally different ways of approximating wave functions. But they're all sort of converging on we can do iron sulfur clusters. Maybe Chan says you can do Fumoko. We're trying Fumoko. Maybe you're trying Fumoko too. I don't know. I guess how can we take these seemingly disparate sets of classical algorithms and their strengths and use that to wrestle with, I don't know, where are they all going to collectively fail so that we could find a place where quantum computers might have advantage? Is that just a bunch of heuristics? Is there something more clever? Is it just size? We're all going to fail at 1,000 qubits?
Yeah, so that's an interesting question. I mean, I don't think it's actually true. They all have an overlapping area, but I don't think it's true that they're like best at the same place. Like DMRG, quasi-1 D things is best. And we scale very well the 2D periodic systems that we know a sum of determinants is going to fall apart. And the sum of determinants is going to be particularly good where like you can get a large enough fraction of the Hilbert space without some sort of. Now your question is like, okay, where is the like union of things really failing for places where you might want to look for quantum computing? And I'm not sure. Maybe big systems is sort of the zeroth order thing. Maybe outside the ground state is even a better answer. Although in practice, even things outside the ground state, you often want to start like pretty close to the ground state. I don't know that I have a great answer.
All right, let's thank Bryan again. Checking this one, so you don't get in trouble again.
Sorry.
Checking this doppel, so you don't get in trouble again.
Oh,
So make sure the mic is.
I am still attached to that.
Thank you so much.
Yeah.
Okay, so do you use PC or do you use?
yes, this is-
I think this guy is.
The black market side is.
Yeah. It's red.
Yeah, exactly.
It's even right now. Barely.
It's conditioned on the so you might be right to do this level.
You have to think how they're measuring. How do you measure it? And like when you're measuring a value, you're just measuring the value of you're measuring
Yes.
and then again. Local. When you're measuring of that, you measure us because it's the projector onto that state. That's the permission operator that you try to measure. Generically, in these, unless you fine tune it very, very much, but then that's something you can do classically if it's fine tuned, like you're.
Yeah, because
They're taking complex, they need large circuits. Non-local circuits, great. You take these operators and calculate their expectation values, they would generically be extremely simple. He says he has more, it's no problem to do it when he does classical simulation. In the classical simulation, you need to actually repeat the measurements. And that's why he says he has more trouble with them. Oh, because when he does the classical simulation of the quantum computer, that's the thing, it doesn't repeat actual measurement. Yeah.
But one of the things you're saying is like, if it's something that I could like write well, projectors, our projectors, something like that. Then you're saying. Anyway.
Yeah, then you don't have to do it. People forget post actually.
Yeah.
Now, when you're talking about time with this it might be. The problem is when they start to talk about it gives the advantage in the scale, then they have to ask what happens when I take
I think the range of people are so weak, like hundreds, right? Like you need sort of.
Yeah. Even then, no, but it's not just the number of orbitals, number of electrons.
Oh, yeah.
You have many orbitals and one electron.
Yeah. Sorry, but then one of them.
Yeah.
Size of the Hilbert.
My number might be 110. Complex states you want. We have your basis state. With the quantum. Station values very, very non-local operating.
I see, yeah.
And also you can only find zero. In some sense, different ways of what and in this case, I think they don't have all kind of all of these. Maybe they're negative. Yeah, yes. I don't know how you get it.
Oh.
Rebooting it to Mac.
Rebooting it back.
Yeah, I'll take that dongle.
I'm gonna lie, I ask, you're essentially like changing the settings.
It's been a long time since I've seen this problem.
Yeah, it's. And so what you see, they made him. Thought everyone was listening to my system already. Weird.
Probably so weird.
Right thing in the week was.
If you're not highly privileged.
I've got cards to flash.
For a while, we were just having it.
Yes.
If the leads down.
Sure, there are places that everything is measured zero fraction of focus.
Okay, great. So our next speaker is Andrew from IBM.
Okay, thanks. Yeah, sorry for it's going by itself. Sorry for the technical noise. Okay, so thank you so much for having me here. It's going to be a bit more of a technical talk. I hope that's okay. But it's also really short. Like I don't have a lot of slides, so there's a lot of opportunity to ask questions and have discussions. And mainly what I'm looking for is this is mostly a theoretical result, but I'm curious if people have ideas for applications, because the motivation is a very natural one. I do this with a kill them. Okay. So the motivation comes from symmetries. So as we know, symmetries have a fundamental role in physics, but also in other fields like mathematics, computer science. And you're probably familiar with a lot of these symmetries. So like physical symmetries, like translation symmetries, rotations, gauge invariance, Lorentz invariance, and so on. And then maybe closer to computer science and also to quantum computing, you can have like permutation symmetry or like relabeling systems. You can have stabilizer symmetries, symmetries derived from local Hamiltonians, and so on. And so, these tend to mean like we sometimes just care about states up to some symmetry, or states that are invariant up to by some symmetry. But we can also care about equivalence classes of states that belong to like the same symmetry class. So this just means that if I have two states psi and phi, I would say that they're equivalent to each other if there's some group element from some group G that can map phi to psi. Okay, and there are many examples of this. So like entanglement structure, for instance, like if you have an entangled state, you can act with local unitaries on that state and it's not going to change the entanglement structure. So any two states that are related to each other by local unitaries will be in this equivalence class of having the same entanglement structure. Similarly with magic, which are related by Clifford operations, polyframes in error correction are related by polymaps, and topological phase, which is not necessarily a group operation, but again is a type of equivalence of quantum states. And so a natural question we can ask is, are two states in the same equivalence class? Or more specifically, how hard is it to determine this? And that's what I'll be talking about today. And to my knowledge, this question has only really been studied from like this complexity theory perspective, only for the symmetric group. But in this work, we're kind of looking at it for pretty much general groups. The results I'm going to be talking about will only apply for finite groups, but we do have some results about infinite groups as well that I'll talk about at the very end. Okay, so our setting will be this. So let's say we fix some group G, which is a finite group, and we have a unitary representation of it, so we can act with group elements on quantum states as unitaries. And I'm going to define this problem, which I'll call the pure state group isomorphism problem. It's a bit of a mouthful, but hopefully it makes sense on an intuitive level. So the intuition, kind of as before, is I want to give you two quantum states and ask you if I can map one to the other with some group operation. But then the question is, how do I give you the quantum states? So because we want to study this as like a problem that's like maybe end-to-end classical, then the classical input will be circuits that prepare these two states. So C1 prepares psi1 when acting on 0, and C2 prepares psi2 when acting on 0. And you have to decide relative to this group G that's kind of implicitly specified, whether there's some group element that when you act with it under this representation on psi1, it maps you to psi2, even approximately. Or if, say, for all group elements, the two states will always be far from each other. So if you do like a group element on psi1, the overlap with psi2 will always be very small. For instance, like a small constant. Okay, so pictorially, this is kind of the question we're asking. So you're given the description of two quantum circuits, like you actually have these two circuits, and you just have to figure out, and you also know what this group is, like maybe we fix it to some known group like Pauli's, Clifford's, or whatever, or maybe it's somehow specified to you as well. And you just want to know, is there a group element that can map this output state of one circuit to the output state of the other? Yeah.
Can I just, when you say small, would I want this number to decrease with the number of qubits in my system? Or
Right,
is it fine if it's just 0.1 all the time?
Yeah, that's a great question. So our results will all hold for a constant. Yeah. But the first condition, the yes case, as it were, there you do want it to be better and better as you increase system size. In particular, for that one, you would like say that the overlap is at least -1/π between like psi2 and R of G applied to psi. We'll explain that in more detail. But yeah, so this is the problem that we're looking at. Yeah.
Can this be solved by just saying that psi1 and psi2, are they in the same URAP or different URAPs?
Well, you don't really know. Like we want to be able to solve this problem in general. Like I just give you two quantum circuits, and you don't even know if they actually relate to the group in any way. And then you just want to determine whether there's a group element that can.
But the group is represented in the space, right? So, and then can't you just answer that question by analyzing which irreducible representations these states require to be represented?
Sure, but you might not be able to do that efficiently.
Right.
Yeah. Okay. So, this is one problem we can look at. We can also consider an analogous version for mixed states, though I won't be talking as much about this one. Where now you're given circuits that act on n plus k qubits rather than just n, and we're just going to trace out k of them. So let's say the last k qubits. Like we fix some register that we trace out, and this gives us two mixed states, row 1 and row 2. And the question is the same, like if I conjugate one of these mixed states with a representative from the group, can I map from one to the other, or is it the case that the states are always far under the action of any group? Okay, and so the question that we're asking is how hard are these problems to solve? And before I can give you an answer to that, let me just do a very quick primer on complexity theory. Some of you are probably familiar with this, but for the sake of completeness, let me just cover this real quick. So P here is supposed to be the set of problems that you can solve efficiently, i.e. in polynomial time on a classical computer. Sometimes we also use BPP if we have randomness, but for simplicity, I'll just call it P here. Then there's NP, which is the set of problems for which you can verify the solution in polynomial time on a classical computer. But finding the solution might not necessarily be efficient. So a canonical example is like, I can give you a graph and I ask you, can you color it with 3 colors such that no 2 neighboring vertices in the graph share the same color? So in general, this seems to take exponential time. But if someone claims to have a 3 coloring of a graph, they can just show it to me and I can check very easily if it's true or not. So these are NP problems. We believe that there are strictly more NP problems than there are P problems, but no one has been able to prove this. It's kind of literally $1 million question that people have not been able to answer, but this is kind of what we think the relationship between the two of them is. So now if we move to quantum, we also have this class called BQP, which represents the set of problems that you can solve in polynomial time on a quantum computer. So this contains everything that we can solve on a classical computer. And it seems to also contain some problems in NP that we don't know how to solve efficiently classically, for instance, factoring. So it's a problem that you can solve efficiently on a quantum computer with Shor's algorithm, and you can verify the solution efficiently by just multiplying the factors. But we don't know how to solve it efficiently classically. Then we can kind of consider, like, now we're going into weirder territory. we can consider a class called QCMA, which is a sort of quantum analog of this NP class. So this is a set of problems for which you can verify the solution, but you need a quantum computer to do it. So it's efficiently verifiable on a quantum computer. And sort of like the proof that you're given for the problem that you're interested in is given to you as a classical string. So it's a classical proof. So for instance, maybe someone claims to have a classical description for like a low energy state of some Hamiltonian. They can give me that classical description. I can use it to prepare the state on my quantum computer, and then I can check if it has low energy or not. So this would be an example of a QCMA problem. But finding that state or finding that description could be hard in general. Okay, there are two more, which are the weirdest of them all. So this one is called QCSZK. Computer scientists were very bad at naming things. So this stands for like quantum classical statistical zero knowledge. And intuitively, it just means the following thing. So if we go back to this QCMA example of like, problems for which I can verify the solution on a quantum computer, QCSZK says you can verify it. So you can verify, for instance, if the answer is yes or no to some yes or no question, but you don't learn anything about the solution. So for instance, maybe somebody claims, again, that like they have a description of like a low energy state for some Hamiltonian, and they're able to convince you of this fact without ever giving you the description of that state. So you never actually learn what the state is, but you're still able to check with very high probability that they do indeed have this description. So these are problems for which we have these so-called zero knowledge verification protocols. So there's also a fully quantum version of this, where now the kind of the proof is a quantum state rather than being just classical strings. Okay, this is the landscape of complexity classes. Basically, what you need to know from this is that BQP and P are things that we think about as easy, so to speak, because you can solve them either on a quantum computer or a classical computer. And then if something is in one of these other classes, then we don't know if it's easy or not. It might very well be hard in general. Any questions? Yeah.
When I took a quantum computing class once upon a time, I learned about QMA.
Yeah.
Is that one of these or?
No, so QMA is a generalization of QCMA.
Mm-hmm.
So in QCMA, I'm saying that like the proof is classical, for instance, the description of a ground state.
Okay.
In QMA, you allow it to just be a quantum state. Like into my quantum computer, I can receive a quantum state and I can test that state. So that's QMA. QCMA is kind of like a weaker version where, it has to be a classical description of the state. Any other questions? Yeah.
It might help if you could specify that whether there are complete problems for these QSZK and QCSZK problems.
Right. That's a good point. I should have added that. So a complete problem for QSZK, so this one, like the gray one, is you're given two quantum circuits and they prepare mixed states. So you like trace out part of the output and you look only at the mixed states. And you're asking if those two states are close or far in trace distance. So this is called the state distinguishability problem. And this one is complete for QSZK in the sense that it like fully captures the complexity of that class. Like every problem in QSZK reduces to this state distinguishability. For QCSZK, as far as I know, we don't know of any complete problems, but one which we might conjecture is a good candidate is you're given classical shadows of two states, and you're asked if they're close or far in trace distance. Other questions? Okay, if not, then here are the results. So this pure state group isomorphism problem that I showed you before, we can show that for any non-trivial group G is BQP hard, meaning that it's at least as hard as any problem that we can solve efficiently on a quantum computer. So any problem that you can solve in polynomial time on a quantum computer, I can always map it to one of these isomorphism problems with respect to some group. And I'm actually going to show you the proof of this statement. So that's sort of like a lower bound on the complexity of this task. What about upper bounds? So it turns out that this problem is contained at the intersection of QCMA and QCSZK, which means that if I wanted to, like prove to you that two states are related by a group element, then I can do that with just a classical proof, but you have to verify it on a quantum computer. That's what it means to be in QCMA. And this is maybe intuitively clear because if I claim to you these two states are related by this group element, then I just give you the group element, under the unitary representation. And, you just run it as a circuit on your quantum computer, and then you do a swap test between the two states to check if they're equivalent or not. So that shows that it's in QCMA. And you can also do this in a way that doesn't actually reveal what that group element is, and that's the QCSZK part. Now, if we look at specific groups or like start adding structure to the groups, then things get a bit more interesting. So for instance, if the group is abelian, then you can show that the problem reduces to something called the state hidden subgroup problem, which is like the ordinary hidden subgroup problem, but the subgroup is with respect to like some quantum state. Again, I'll explain this in a bit. And it reduces to this problem with respect to what's called the generalized dihedral group. So it's like G and product with Z2. And finally, if we look like at super specific groups, then for the poly group, it's actually contained in BQP. So we can solve it efficiently on a quantum computer. Because it's also BQP hard, it means that it's complete for BQP. So this means that like deciding if two states are related by polys is something that fully captures the complexity of what we can do on a quantum computer in polynomial time. On the other hand, for the Clifford group, which is another like natural group to study, it seems that the problem is at least as hard as something called graph isomorphism. This is the problem of being given two graphs to determine if, by just permuting the vertices, I can map one graph to the other graph. This is a problem that we don't know how to solve efficiently, classically or quantum. So this seems to suggest that like the Clifford version of the problem is hard even for quantum computers to solve. And finally, this mixed state version of the problem, it's kind of the easiest, so to speak, to classify because it's just complete for this QSZK class for all groups, like irrespective of what your group is, the group structure essentially doesn't matter. The problem is just always going to be very hard, basically. Okay, so, I won't have time to go through all of these, but I'll go just through two of these results. So first, let me show you how we prove that this problem is at least as hard as any problem that you can solve in polynomial time on a quantum computer. So the idea will be that, if I have some circuit C, like some polynomial size circuit that is solving some problem in BQP. And let's say this is just decision problems, so like yes or no problems. Then what I want to show is that I can take this circuit C and map it into an instance of this isomorphism problem, which means that if I can solve the isomorphism problem, then I can solve my original problem from BQP. And the way I do this is as follows. So I take this circuit C for which, say I want to decide if its output is, sorry, I skipped a step. So with this circuit C, if say the answer to the question is yes, then when it acts on all zero, it's just going to output all zero, or it's going to output a state that has very high overlap with all zeros. And if the answer to the question is no, then it's going to output a random state. What do I mean by a random state? Basically a t-design state. And we're going to pick this t-design state, like this t, to be polylogarithmic in the size of the group that we're considering. This is why it's important to work with finite groups. Okay, so why do we do this? Well, because now I can consider the following problem. So suppose I take my circuit C1 in PSVI to be just this circuit C that's solving some generic quantum problem. And C2 I just take to be the identity circuit. So this means that the state psi1 is either going to be all zeros if the circuit answers yes to its decision problem, and it's outputting all zeros. And if the answer is no, then it's going to output this t-design state, this phi state. Whereas the other state, psi2, is just always going to be the all zero state. And now you can see that if the answer to the question is yes, then both of these states are all zeros and they're trivially related by identity. So the answer to the isomorphism question is yes. On the other hand, if the answer is no, there's no group element that can map the all zero state to this T design state. That's why it was important to choose T to be of this form. It's kind of like saying that like no group element can map all zeros to like a totally random state that I picked as a function of this group. Okay, so this shows that in general this problem is at least as hard as anything I can solve in polynomial time on a quantum computer. Well, that's not the low condition. But now let's look at a specific example, which is the poly group. So I already showed you that we have this lower bound of PQP. Now we also want to show that we can actually solve the problem in polynomial time quantumly for the case of the poly. So I'm going to take a simplified version of the problem just for ease of presentation. But the general version will still, like everything will still work. It's just that the calculation will be a bit harder. So the simplified version will be that in the yes case, I will assume that there's a poly which exactly maps one state to the other. So there's some poly P such that P acting on psi1 gives you psi2. And in the no case, I'm going to assume that any poly, when you act on psi1, the overlap with the other state is basically negligible. Like it's exponentially close to zero. Okay, so I need to give a quantum polynomial time algorithm to solve this problem. How will I do this? So if I have the circuit C1 and C2, I can efficiently construct this state, which is an equal superposition. So I have ket0 and psi1, ket1 and psi2. So this is like saying I create a plus state, and then controlled on 0, I run the C1 circuit, and controlled on 1, I run the C2 circuit. And I get this thing. And now notice that if the isomorphism exists, so if there's a poly P that maps psi1 to psi2, then this state phi is invariant under the action of poly X tensor this poly P. And that's because P will map psi1 to psi2, and poly X maps 0 to 1. So it just flips these two components in the superposition. So it leaves the state invariant. So I've constructed a state that's basically invariant under the action of this pole, effectively. So that means that there's a stabilizer subgroup of the polys, which stabilizes this phi state that I've constructed. And so we just need to find an element of this stabilizer subgroup. So we just have to solve this state hidden subgroup problem for the poly group. And there's a problem, which is that the poly group is not an abelian group. And the hidden subgroup problem is something that generally we know how to solve only for abelian groups, quantumly in polynomial time. But there's a way we can fix it, which is that we can make the poly group into an abelian group without really changing too much of the structure. And that's by taking 2 copies of each poly. So this is because polys, they either commute or they anti-commute. So if you take 2 copies of them, they will always commute with each other. So the 2-copy poly group is an abelian group. And so instead of the state that I showed you previously, we're just going to prepare 2 copies of each of the 2 states in the superposition. You have like 0, 2 copies of psi1, 1 and 2 copies of psi2. And again, if the states are isomorphic, then X tensor 2 copies of P is a stabilizer for this state. And now you just have to solve the abelian subgroup problem for this 2-copy poly group, which is an abelian. And you can do this with weak Fourier sampling. So you do basically phase estimation as you would do in Shor's algorithm. And this will allow you to recover elements of this subgroup. And then you can just check with the swap test that indeed they satisfy the condition. And you can also show that if the states are not isomorphic, then with very high probability, the step will fail. So it will either not give you a stabilizer group, or it will give you something that does not stabilize the state. And you will see this when you do the swap test. Okay, and as I said, like this argument can be made robust. So you can make it so that like the overlap between the 2 states can be 1 minus 1 over poly instead of just exact. And in the no case, we can allow any constant error. Okay, so let me wrap up. That's all I have time to tell you about in terms of the results. So there's one annoying thing that you might have noticed from this previous proof, which is that strictly speaking, the condition we require in the yes case when the states are isomorphic is that the real part of the overlap between group element acting on psi1 and psi2 is equal to 1. Because if we said instead, like say the absolute value of this thing is close to 1, well, that can allow for arbitrary phases to be there. And then you would get a phase in this superposition, and now the state might no longer be stabilized by the poly. And then this argument breaks down. So the condition that we actually require is this one. But just before this talk, I asked ChatGPT about this, and it suggested a way to fix this, which is to, instead of just using psi1 and psi2, because you have the circuits, you can also prepare their complex conjugates. And if you do that, then when you act with this, it's going to eliminate any phase that might appear. So in fact, you can, assuming we double check and this actually pans out, you should be able to take this to just be absolute value instead of just the real one. And the reduction from this pure state group isomorphism problem for abelian groups to this state hidden subgroup problem over the dihedral group follows a similar logic to how I showed you this algorithm for the polygroup, like constructing the state that is invariant under some group operation from the dihedral group. So in the paper, we also looked at different ways of representing the states rather than being given as circuits. So in particular, we also said, like, what if I give you the state as like a polynomial combination of stabilizer states? So in this case, the problem becomes much easier, like it's just contained in NP. But we can still show that for some groups, like the Clifford group, it's still at least as hard as graph isomorphism. So it does retain some hardness even in this form of representing states. And we also get that like this state hidden subgroup problem, because of this connection to the isomorphism problem, for the mixed state case, we also find that the state HSP for mixed states should also be a hard problem. This was an open question in a recent paper by Isert and others. And as I said, we also derived some analogous result for infinite groups acting on bosonic states, but I won't have time to get into that. So let me just wrap up with some open questions. As I said in the beginning, I think one of the main open questions is what applications can we find of this thing? So like what situations are there in the real world where we would care about something like this? And what can we say in that particular situation? Also, how much does the group structure actually matter for these results? For the upper bounds, it seems to matter a lot, but for the lower bounds, we don't think it matters. So we think, for instance, for topological phase, you can probably prove analogous lower bound results like BQP hardness and so on. And finally, it would be nice if we could get an even better characterization of the complexity for the pure state case, as we do for the mixed state case, where essentially we know it fully, like we know its complexity in the mixed state case in general. Whereas for the pure state case, we have these upper and lower bounds, but they don't exactly match. Okay, so with that, I'll end here, and I'm happy to take any more questions.
All right, any questions? Yeah, go ahead.
Yeah. In your hardness result, is there like a dependence on, so it was stated as for non-trivial groups, but does that mean that the group can be even like constant size?
Yes.
Okay. It just has to have, I guess, a representation that has like a large size, right?
No, actually, it doesn't matter, because for the BQP hardness, you're essentially encoding the hardness in the circuit. So even if the group is constant size, like you might imagine, oh, I'll just enumerate over the group elements. But you still have to, decide whether a circuit outputs all 0 or not. And this requires solving a BQP problem. So for constant size groups, it might also just be in BQP, because you can enumerate and just test for every group element. But it's still at least as hard as BQP. Yeah.
On your last slide, you mentioned the dihedral subgroup problem.
Yeah.
Does this have implications for, I guess, lattice-based crypto methods? Because I think solving the hidden subgroup problem over dihedral groups solves that, right?
Yeah, that's a good point. So I don't know if it directly connects to crypto. It's just that, both of these situations, like, if you can solve the dihedral subgroup problem, then you can break crypto, and also you can solve the abelian pure state group isomorphism. But it's not clear if, the abelian pure state group isomorphism itself relates in any way to crypto. But I think that's an interesting direction to explore. Yep.
So the state HSP was introduced in relation to this question about detecting an entanglement, right?
Yes.
Does this problem kind of shed any new light on that?
Yeah, it's a good question. Like we did think about it a little bit, but we didn't find like anything concrete to say about it other than this thing that I mentioned at the beginning, which is that if you have two states and you want to determine if they have the same entanglement structure, then this is an instance of this problem where your group is just local unitaries, like like n copies of SU, SU1, SU2.
Okay, I think we're gonna wrap up. We have 25-ish minutes for coffee. We're back at 3:35. Let's thank our speaker again.
Oh.
Yeah. When I saw one, I guess there's a guy. One is asking what should we do in the dinner. Yeah. I strongly believe that all these radios should be unified by all scientific methods.
Everything is- everything is-
I should have. Slide that I should have. I just wanted to find very.
You want to measure it. It's still free. We function. So that's one cost.
That's what we go by. Many years.
It seems very difficult to have a model that can't get upright.
Yeah.
Don't put it in the pocket.
Okay, we'll get started. So our next speaker is Makrand Sinha from the University of Illinois.
Hi, it's the University of Illinois Urbana-Champaign, and we've been trying to rebrand for the last 10 years, but I don't think it has been successful. So anyway, so this talk is based on joint work with Alex Poremba, Tony Melker, and Henry Yuan. And I think since we put out our paper, a lot has happened around these questions I'm going to talk about today. So I wouldn't feel right, if I didn't mention these works. So I thought, I decided to make it a survey, and I will talk about some of these other developments by other research groups as well, maybe for a few minutes at the end. All right, so I was told to always start my talk with a joke, if possible. I came up with a joke, but it's a very nice joke, but it's not going to make sense until the talk ends. So I'm going to tell it now, and hopefully it will be funny at some point in the talk. Yeah, so if you want a tagline to remember this talk, permutation function and a Clifford walking into a bar. The bartender says, looks hard to me. This is very funny, but all right. So I'm a computer scientist. So one of the major things in computer science is this idea of de-randomization. So you have some ideal random object. It uses a lot of randomness sort of generate, to store, to work with. So often in applications, we want to sort of use a pseudo-random object that works just as well for our applications. So there are two sort of different notions of pseudo-randomness that are very natural. And these are, one is the information theoretic notion, and one is a computational notion. And today I'm going to talk about both of those. But instead of this just being abstract, let me try to sort of give you a concrete example for each of these things. All right, so one of the ideal random objects that will be important in this talk is a classical object. So hold, I know this is a quantum workshop, but we'll get to the quantum in a second. So it's just a random function. So you have a function from that maps n bit strings to plus minus 1. So you can think of it just as a long array of plus and minus 1s of length to the n. And this is a uniformly random function, meaning that for every input, you choose with probability half whether to map it to plus 1 or minus 1. So this array is just each plus minus is chosen with probability 1/2 is a random coin flip. So this is a very expensive object. So you need like 2 to the n bits of randomness to sort of produce this. And there's sort of two different notions that have been that the field has come up with. One is called t-wise independent function, and the other is a pseudo-random function. And I will try to explain them one by one. So t-wise independent function is another random function. So you can again think of it as a list of plus and minus, this array. But now this pluses and minuses, they're random, but they're going to be correlated in some way. But what you want from this is a t-wise independent, meaning that if you zoom in on a small part of this array on like a subset of t inputs, then it's going to look completely random to you. So unless you look at t plus 1 bits, you cannot do anything. You cannot figure out any difference between this thing and a completely random function. And this is sort of what I mean by information theoretic. And for the rest of this talk, efficient will just mean polynomial time in n, little n, which will eventually be the number of qubits, just to set the stage. So this notion is very useful in computer science. If you take the first algorithms course, it's used in very basic algorithms like hashing. And we know how to sort of construct these objects, by which I mean that we know how to sample them efficiently by a small circuit. And this is very useful usually only when we know t ahead of time. And t is typically small, like 2 or 3 or 4, or maybe even log n. So those are the sort of instances where this is useful. Yeah. And by the way, if you have any questions, feel free to stop me anytime. And the other notion is the notion of a pseudo-random function. Again, it's a distribution over random function, but I will think of it in the following way. You're given a class of functions indexed by some parameter k that I will call the key. And you will just choose this key uniformly at random, and that's how you choose the random function from this family. And the property is that if you know the key, then you can compute this function very efficiently. So there's a small circuit that computes this function. But what you want is that if you don't know the key, and you are just talking with this function, evaluating this function at different points, then you cannot tell whether this is a truly random function or the function you came up with by any efficient algorithm. So you can look at this input. You can choose to look at another input after that and another input, and it can be chosen however you want. But as long as the algorithm runs in polynomial time, it cannot tell the difference. And again, so for these things, we unfortunately don't know how to construct them without any assumptions. Because if you do that, you will prove that P is not equal to NP, and that will be a very big deal. And we're very far from proving it. But we can sort of give efficient ways of constructing them, assuming certain cryptographic things, okay, such as one-way functions. For this talk, it's not really important what these are, just that if you have cryptography, classical cryptography, then you can construct these functions. And they've been very, very influential since they were introduced in the 1980s. And if you know how to build them, then you can build many other cryptographic things from them. So they have been very, very useful. Right. So that's just sort of the setup of what it means to be pseudo-random, at least in these two different ways. So this is a computational notion because here you are, if you allow all possible algorithms, then you can definitely tell these two functions apart. If your algorithm runs in exponential time or infinite time. But if you only look at polynomial time algorithms, then you cannot distinguish these cases. Right. So let's meet the main characters of this story. So here, let's talk a little bit about quantum pseudo-randomness. So our ideal random object is going to be a Haar random unitary on n qubits. So this is just the unitary on n qubits that's sampled from the Haar measure on the unitary group. And the catch with this is that if you want to implement such a random unitary, typically it will require exponential size circuits and also exponential depth if the number of ancillas is kind of small. And the two notions that are information theoretic and computational that sort of arise in this situation are unitary T designs and pseudo-random unitaries. So I think maybe people here are familiar with unitary T designs. And this is the pseudo-random unitary is a sort of a relatively new notion. But let me define them both in case someone doesn't know. So a unitary T design is the analog of quantum analog of a T-wise independent function. So again, suppose you have a quantum state rho, and you apply like T copies of the unitary, T tensor copies of the unitary on the state, maybe on some of the qubits, not all of them. And you don't know which unitary you're applying, so you get a mixed state, which looks like a mixture where you take the average over use. So this is a quantum channel, and the guarantee for unitary T designs is that this quantum channel looks the same, more or less, whether you apply a truly Haar random unitary, which is very, very complex, or a unitary that is a T design. And that's what I mean by they match the moments. Again, there is some subtlety here that is very hard to satisfy exactly, so you have to allow approximations. And there are different notions of approximations, additive error, multiplicative error, which I will sweep under the rug because it's like, I think, almost 4 p.m. and I want to keep it simple. Right. Questions?
Can I just make sure, moments, can I think of these as correlation functions in finite number of?
Yeah, so if you can consider this matrix of moments where you're just computing entry-wise moments of all entries. If your n by n matrix is n squared by n squared matrix. So if you want exact definition, then you can just say that these two matrices are kind of exactly the same. But when you allow approximations, then you have to consider what notions of approximation make sense, and this is more natural there. But yeah, you can just think of it as all the moments, entry-wise moments match up if they're exact. I hope that answers your question. All right, we continue. So again, this is a sort of a relatively old notion. It's been around in quantum information for 2 decades. It has applications in sort of benchmarking quantum learning, which probably people here know more about than I do. Right, so this is an analog of information theoretic notion. And this other computational notion is a notion of a pseudo-random unitary. And this is relatively recent, introduced by a paper by Gheorghiu and Song in 2018. And this notion is very similar to the definition of a pseudo-random function. So again, you have some you have some key k, and you want that if you know this key, then there is a small circuit to apply this unitary to any input state you want. But if you don't know this key k, then no efficient quantum algorithm can sort of tell whether you are in a situation where you're querying the unitary you have, or whether you're querying a truly random unitary. So these two cases look kind of indistinguishable to you. So again, this is a computational notion because you're only limited to like polynomials and quantum algorithms. While these things are relatively recent, they have some applications in, like, they were introduced originally for quantum cryptography, motivated from some applications in cryptography, but they have some applications to many body physics, and recently they've been used to model like chaotic quantum systems like black holes, because you want something that looks from outside to be almost like a hard random unitary, but you still want that nature can do those processes in polynomial time. And this is a natural sort of way of modeling that. And hopefully more applications to physics are there, but we have to discover them. Right. So let me come to the main point of the story, which is, so you have these two different objects that I've just defined. How do you actually, efficiently sample them? How do you construct circuits that are small to sort of implement these things? So one natural attempt to do this is through random quantum circuits. So if you just take a quantum circuit, you add 2-qubit hard random gates, and let's say enough of them, like polynomial in n and this parameter t you want to implement. Then Brandau, Harrow, and Horodecki in 2016, they showed that these are actually, these look like a hard random unitary in terms of its moments. So they're approximate T designs. And there is a lot of work which I'm going to talk about or improving the efficiency of how many gates you need here. And one can also make a conjecture that if you take enough of these gates, this random circuit, enough depth, like say polynomial depth, then this gives you a pseudo-random unitary on n qubits. So this is a very natural conjecture to make, and I will come back to this at the very end, the thought. But again, if we prove this unconditionally, it implies something like P versus NP. Not exactly the same thing, different thing, but it will imply like two different complexity classes are not equal, which at the moment we were very far from having any ideas of how to prove such things. So to build such a pseudo-random unitary, you need some cryptographic assumptions. And the question is, suppose we can assume cryptography, can we build these objects? So there's a long line of work on sort of trying to give more efficient unitary designs. And I'm not sure I got all the references, but because there are tons of them, but I tried my best. But for this other notion of pseudo-random unitary, even if you assume cryptography, until recently there were no actual constructions, there were only candidates. And there were some works that sort of made partial progress on some restricted types of inputs, but the original question was open for a while. So this is the sort of what we did in our paper. We introduced this thing called the PFC ensemble, and hopefully by the end of this slide you can understand the joke and maybe you'll find it funny. So sort of this is the main message of this talk is we have these very nice objects in the classical setting that we known how to construct for like 5 decades or 4 or 5 decades. T-Bus independent functions, pseudo-random functions. Can we use those constructions and try to port them to in a black box way to build these objects we want in the quantum setting? And we sort of gave a way to construct both of them in a unified way. So this is a very modular construction. You get both of these things by sort of instantiating properly. And to do this, we need 3 different objects. We need a random permutation that permutes all 2 to the n bit strings. So this just permutes all the qubits if you apply to a basis state. You have a random function, the random Boolean function. that when you apply to a basis state, it just adds a phase f of x in front of the state, which is plus minus 1. And you need a random Clifford from this Clifford group, which we have known for a while that is an exact 2 design. Okay. So if you have these three different objects, a permutation, a function, a Clifford, then our main theorem basically says that if you take the product of these 3 matrices sampled in this way, then you almost look like a hard-random unitary for exponentially many moments. So the moments match up more or less up to like 2 to the n over 2. Yeah. So that's the sort of the main sort of theorem that we prove. Yeah. 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 You are asking the question which I'm going to answer. Maybe you can look in the future. So. Right. I should also say that there was another independent work by Chen, Bulan, Brandau, Dr. Hayden, and Zhu, who gave a different sort of construction based on exponential sums of random permutations. But yeah, I'm not going to talk too much about it. All right, so let me come back to the joke. Hopefully you can look at it and maybe find it funny. I don't know. There is a reason I didn't go into stand up. So, all right. So now to answer Brian's question, there's still a catch here. We have come up with a way to give this unitary design, T design, but you are still like using a random permutation and a random function to build them. And these are very complex objects. So you can, if you want to implement them with a quantum circuit, they will still need exponentially sized circuits. So what have we gained? And the sort of the main punchline is that if we replace these classical objects, a random permutation and a random function, with their pseudo-random counterparts in the classical world. So if you replace these random permutations with t-wise independent functions and t-wise independent permutations, which we know how to construct, then we get T designs in this very modular way. And not only that, it turns out that this gives you, at least at that point, the best known constructions of T designs in terms of size and depth. And if you replace them with their pseudo-random counterparts, pseudo-random permutations, pseudo-random functions, then you get these computational notions of pseudo-random unitaries. Okay, I don't know what privacy agreements I have to accept, but I will continue. Yeah, so if you replace them with their pseudo-random counterparts, you get a pseudo-random unitaries. And we did manage to kind of prove the most general result. We managed to prove that pseudo-random unitaries, what your distinguishers had to be somewhat restrictive. They were non-adaptive. They only made parallel queries. And we could handle adaptive algorithms by allowing some extra ancillas. But the story is becomes very satisfying by a sort of a later paper of mine, who introduced a very nice technique that I don't have time to talk about. But they actually managed to prove that it actually gives you a pseudo-random unitary. So, which makes this at least picture very, very nice for me. All right, so that's the main sort of message of what we did in our paper. And I'll pause here for a question.
It's still it's a PRU under the assumption that the functions are they're still computationally.
Yeah. So you do have to assume that you have you know how to build pseudo-random functions from some classical cryptographic assumptions. Yeah. So under those assumptions, you have a PRU. Yeah.
Did mine one have to do CPFC for this generalization?
Sorry?
If they have to add a Clifford on both sides to get the adaptive security?
No, I don't think that's needed for this. Yeah, that's for something else, I think.
That's a different, okay.
Yeah, that's a slightly different models if you, but yeah, I can tell you about it later. There are too many things, definitions. Okay, yeah, let me continue. So there have been some other very nice, amazing results after our paper came out, and I just want to, mention them briefly. And again, this is not going to do my work, so if you have any questions, maybe some of the authors are here, and you should try to ask them the questions. And the first question that sort of there is an amazing progress on is the question, what is the minimum depth one needs to build a T design? What's the shortest possible depth you need to generate T designs? Sort of relevant practically because you need small depth computations, otherwise things are not coherent. So this was a sort of a very natural question from both theoretical and practical standpoint. Okay. And whether you need log n and square root n or n to the 1/4,
sorry, you're thinking of T as being fixed finite or?
Yeah. For now, it's just I'm thinking of it as a constant, but the actual bound will depend on T as well. Yeah. So at this point, people thought that let's consider a 1D brickwork circuit. So you only have nearest neighbor gates. Let's say they act on 2 or 3 qubits, maybe constant number of qubits. So if you have a circuit of depth, let's say n over 100, each qubit can only affect the light cone is only very small. It can only touch like a few number of a small fraction of all the qubits. So it seemed like our construction already gave a linear depth T design, so it seems like maybe this is the best one can do. But in a very surprising result, 2 different independent works actually showed that the answer is like log n. So Schuster, Haferkamp, and Huang, and independent work by Levitsky and Lara Quente, they sort of showed that you actually get T depth, T designs and sort of log depth, where n is the number of qubits here. Yes. So this was very, very surprising at the time. And let me mention the key sort of idea of this paper by Schuster, Haferkamp, and Huang. And this is called the gluing lemma. This is very, very nice. It allows you to do many things. It's very, very modular. And basically what they showed is that suppose you know how to construct T designs on small number of qubits. Let's say you can compose them by applying them one after the other in some slightly offset way so that a small number of qubits overlap. Then you get a much bigger T design. And the overlap can be very, very small, can only be logarithmic. And that's enough for this to be a much bigger T design. So this is the key lemma that they proved. And why this helps is that suppose you manage to construct like small T design log n qubits. So each of these black boxes is a small T design on log n qubits. And you put them in 2 layers, and they overlap and also log n, small number of log n qubits. Then you can glue them one after the other and apply the previous lemma, many times to show that this whole circuit forms a T design. And now the only problem that remains is like, how do you instantiate each box? But each box is only log n qubits. So we reduce our problem to generate a T design from n qubits to generating a T design on log n qubits. So then you can bootstrap it by, using a different sort of T design for these smaller boxes. So you can use the PFC design on these small qubits. This will give you a way to construct T designs. Later work by Chen, Ha, Haferkamp, Edgar, and Tan. They proved some other amazing result, but one consequence of their result is that you can also take each box to be just a random circuit with 1D brickwork architecture. But if you arrange these boxes in this way, you get a T design in log n depth. And this is a sort of a very, very nice result. And let me also mention another interesting result, which is by Key, Schuster, Randa, and Huang. They actually constructed a different variant of this PFC ensemble. So instead of a random permutation, they used the more structured permutations in some way. And this allowed them to sort of prove some other interesting results, which I will very briefly mention because I don't know the details here too much. So if you use the previous lemma with these instantiations, you get T designs that are exponentially improving in both parameters. It's log of T and log n and the number of qubits. And it's not true. You do have to assume something about the circuit. You do have to assume that you have gates which can act on any 2 qubits, and you have ancillas. Without them, the situation is a little bit different. And they also used it to prove, something about black holes and how fast they scramble information. Just want to mention that there have been some applications of these objects to physics, but hopefully there are more, and I will be interested to hear about what you think, because I think computer scientists don't know anything about physics, so we can't come up with these applications. So we do have to talk. If you have any ideas, I'll be very happy to hear them. Okay, so that's essentially, as far as I know, the latest developments, and I've only sort of focused on things that are very closely related to what I was talking about. I know many people have worked on T-designs, and there are many interesting questions that still remains about them. Right, so I have maybe 3 minutes left, or 4 minutes left. So let me just conclude with sort of why are we so excited about this, at least in computer science. So again, this is applications to physics, but one of the reasons like computer scientists and in particular cryptographers are excited about it is because of this possibility of doing quantum cryptography in Algorithmica. This is the title of one of my papers, and I just want to explain what this means. So if you want to do quantum cryptography, most quantum cryptography still requires assumptions similar to classical cryptography. Like factoring is hard, or even more specialized assumptions like learning with errors is hard. There are some exceptions like quantum key distribution or BB84, which don't require any assumptions. But most quantum cryptography that we knew how to construct seem to require these classical cryptographic assumptions. For instance, we saw that if you assume like pseudo-random functions or one-way functions, then you can construct these pseudo-random unitaries. But you can ask, okay, suppose we lived in this world where P is equal to NP. And again, it doesn't really matter if you know what these complexity classes are. This world is called Algorithmica. This is a hypothetical world which we could possibly live in because we're not clever enough yet. But in this world, if you live in this world, you can solve many hard problems in polynomial time. You don't need a quantum computer to break RSA. You can just do it on your laptop because it's in polynomial time. So even if you live in such a world, is quantum cryptography possible? And there are things like quantum key distribution that are still possible. Are there more such things that are still possible? And in a line of work started by William Kretschmer, and together we had with Kretschmer, Kian, and Tal this paper, Quantum Cryptography and Algorithmica, which basically showed that quantum cryptography and other applications are potentially still possible in this world. And again, there is some asterisks here because this result is hard to explain what it means to people who are not computer scientists, because it's proven in some idealized model, which doesn't really translate to the real world exactly, but it gives us some hints about the real world. So the question that's left open is like, can we find real world assumptions that give us quantum cryptography, but without giving us classical cryptography? So meaning that the task that we come up with to base our cryptography on is something that's inherently about quantum data. It doesn't really encode somehow secretly a classical problem inside it. That's another way of thinking about it. And this is not an easy assumption to come up with. People have tried to come up with many candidates, and you can try yourself. It's really hard to satisfy both of these things together. Or one candidate that's still open, and that's as far as we know, it's still stands, is this candidate that random quantum circuits of a polynomial depth. They are pseudo-random unitaries. But as I mentioned before, if you prove this conjecture, you will prove something strong in computer science. So, which we are very far from proving, at least. I don't know whether ChatGPT will be able to solve this, but we'll see in a few years. But the question, but again, this is assumption, and cryptographers, if you want to do something in cryptography, you have to really test your assumption really well, because you don't want some hacker to break your crypto system. if it's like a bad assumption. So can we actually give more evidence that this is true? So here's one natural question. What statistics of random quantum circuits? What problems about them one can solve efficiently? And also its flip question, can you build useful cryptography from random quantum circuits that one can implement and use in practice? This may lead us to some other new applications of quantum computing. There have been some recent lines of work which actually try to build cryptography from random quantum circuits, including a paper of mine with Bill and Stromik and Henry. And I think recently the JP Morgan Chase lab, they actually implemented some of these cryptographic schemes and demonstrated that some of it can be done on current devices as well. Although the applications are not really very, very practical, but it's like something that can be done feasibly in current hardware. But whether it's of practical and economic value, we don't really know. So I think I will end here. Thank you very much.
Okay, we have time for a couple of questions.
Yeah. Is it feasible in a minute to give some examples of quantum cryptographic primitives in the world of Algorithmica that don't have, well, in the world of Algorithmica, I guess we don't have classical cryptographic primitives. So
You can take 3 minutes if that helps.
3 minutes.
it's fine if it's not doable.
I mean, I'm just trying to think of interesting, primitives, and I would say that I don't think we have really interesting primitives. Something that you would actually use in. You would have some
primitives that are surprising that they even exist, even if they're not useful.
I mean, one notion is like a bit commitment, where it's basically like something where you put a message in a box, and there are 2 different stages. And in the first stage, until you open the box, the message looks random to you. But then you send a message, and then you can distinguish whether it's 0 or 1. And that's something you can do quantumly, because it reduces to something about distinguishing quantum states. And that's something well, I mean, it's really hard to explain what it means to not be classically. You can also do it classically, but you cannot do it classically if physical to NP. So that's what I mean. So I don't know whether that answers your question, but that's
very much so. Thank you.
Yeah. All right.
Last call.
Is that the kind of answer you were looking for when you say, when can we get assumptions that give quantum cryptography with someone else? I can't even imagine how an answer to that would look.
No, just like this is one candidate. I mean, we don't know how to construct classical cryptography from it, and there's some evidence that it truly lies outside, assuming some conjectures in quantum advantage, that it truly lies outside NP. But again, what I'm not sure is like what sort of useful cryptography you can build. So at the moment, the cryptography is like very basic. You wouldn't want to implement these things in real life, and because I mean, cryptographers don't really believe we live in. They believe we live in a world where one-way functions exist. So why would you want to do this? But maybe it allows you to do things that you cannot do classically, like quantum money. So that's the dream. But yeah. Anyway.
Yeah. Regarding the gluing lemma, we generate approximate T design for log n qubits and to glue them into the n qubit T design. What's stopping us to recursively applying it? Like when we generate approximate T design for log n qubits, we may try the same trick so that the depth is log n, something like that.
So first of all, yeah, I mean, what's stopping us is like when you glue this, the errors add up, and if you have log n boxes, the error parameter you want it to be like 1 over n-ish. So you need to set the epsilon to be, at least 1/n, and that's why you stop at log n.
I see.
But you do get log n if you allow all-to-all connectivity. So, yeah. So, but you need ancillars for that.
Thanks.
Okay, let's thank our speaker again.
Our final speaker of today did us a favor and swapped in today. And so our last speaker, Abhinav from IBM. And as soon as the slides are up, we'll start on the school. Which is on hold in case we need our help. I think we're good. Okay, great. Voice yours.
Okay, thanks everyone for coming, and thanks to the organizers for the invitation. It's really great to be here. Yeah, today I'm going to be talking about conditionally peaked circuits through error correction. But yeah, our focus in this work is coming up with cases of or proposals for a verifiable quantum advantage. And this is joint work with a lot of folks that you see here in the audience. Shomeng Ghosh, Will Pfefferman, Michael Gullens, and Dominic Hangleiter. So let's begin. And the broad motivating question is, what is our best evidence to date that quantum computing confers upon us powers that lie outside of classical, or as I'd like to think of it, wizards versus muggles, right? And there's a lot of interesting work in this direction, which is somewhat along the lines of, if our model for quantum computing is correct and indeed realizable in our physical world, then we have good theoretical evidence for the statement that quantum computers cannot be simulated by classical computers. So then the broad question is then, if we believe this complexity theoretic conjectures, then aren't we done? So you might ask, why do we even want to perform these experiments that purport to show quantum advantage? And it's worth thinking a bit about this. And here's some answers I like. One, it kind of probes the validity of quantum mechanics in this so-called high complexity regime. And it's also a meaningful milestone on the path to building a useful quantum computer. And there could be other reasons to answer this. Please let me know if you have other answers to this. But assuming that these are the answers we care about, it also means that the way we certify whether quantum advantage happened or not in an experiment it should be device independent, in the sense that it should not rely on the validity of quantum mechanics in the first place. Moreover, the architecture should be scalable in principle, because when we invoke complexity theoretic conjectures, these are necessarily asymptotic statements, and no finite experiment can certify or validate a statement of this sort. So the best you can do is build up evidence by probing larger and larger system sizes. Okay, and Scott Aronson has a nice set of criteria that verifiable quantum advantage should satisfy. And the first one is whether it's near term, like whether you can do it today or not. Another is that these experiments have to be efficiently verifiable on a classical computer. And moreover, there should also be reason to believe that a scaled up version of that experiment can, in principle, be hard to simulate classically. And I'm not right now fully convinced that there are candidates that meet all these three. So one sort of set of experiments that the community has invested a lot of time in analyzing is random circuit sampling. And we don't yet know of good ways to efficiently verify these. So that does not lie in this box. Recently, there's some work on out-of-time ordered correlators. And the verifiability claim here is a bit kind of tangential to what we claim, which is that, it's claimed to be verifiable on a different quantum device. So, so it's not classically verifiable still. And then there's another candidate of peaked quantum circuits, which would be a nice candidate if only we knew how to construct them.
Not in this set is something more like simulating nature and then going and measuring nature. So a molecule, a human builds a molecule, measures some quantity from the molecule, spectroscopic function, some peaks, and then runs a simulation of that molecule on a quantum computer.
Right.
Would that sort of trust in another quantum device because the molecule itself is considered a quantum device?
Yeah, I think I would let that one slide. I mean, if it is indeed the case that we are at a point where there is something in nature that we can also mimic on a quantum computer fairly well, I would be willing to count it. I think those, like the best algorithms for those are still not so near term at the moment.
Yeah, so I agree that's not near term, but I was sort
right.
of wondering whether it counts as classically efficiently verifiable or not.
Yeah, it's not, I would not call it classically efficiently verifiable because you're not doing the verification on a classical computer as such.
Thank you.
Sure. Okay, so let's get to what we do in this work. So we give a scheme that aims to bridge these gaps, but we do not completely resolve this trifecta. So particularly, it's sort of efficiently verifiable, meaning that there's a collection of tests that verifies aspects of the output, but does not completely verify the output. We have, in principle, advantage from a scaled up version of these experiments. And it's not really near term, but near term-ish, which is actually even better, in a sense that I'll get to later. Okay, and this work is a variant on the peaked circuits. So let's go into what people were hoping to do with peaked circuits. And this is the work of Aronson and Jean that motivated or began this line of work. The idea is that have a quantum circuit C whose output distribution, say when you measure in the computational basis, is promised to have some large peak somewhere. So in particular, if you look at the probability of some bit string X, then for some particular one X star, the output probability is large. Maybe C is like 0.1 or something. And let's say someone gives you a circuit where this is promised to be the case. And apart from this constraint, C is otherwise random looking. And the computational problem is, given circuits C that are randomly drawn either from an ensemble, like a peaked ensemble like this one, or just random otherwise, decide which is the case. And quantumly, you can just run the quantum computer and like collect samples and see if you draw one particular bit string again and again. And so you could always just decide quantumly whether they're drawn from a peak circuit distribution or something more random looking. So there are like some problems with this, which is that we don't know of a way to randomly generate circuits that look like this, while also knowing like a lower bound on this peakedness parameter. And we also, like, perhaps you could do something like you have like a deep circuit and then you apply its inverse U dagger. So that will be guaranteed to be peaked, but you also want a circuit like that to be hard to distinguish from random circuits.
Sorry, is it important that you're here, if I understand correctly, you're sampling from a distribution of circuit? Is that important, or do I just need a single peak circuit that?
Yeah, you could construct a candidate that where it's one particular circuit, but for the complexity theoretic part, it makes more sense to have like a whole slew of instances at different system sizes. Yeah. Okay, and also, yeah, this implicitly means that the string that we are going to be highly peaked on, namely X star, should also be hard to guess, just based on the circuit description alone. So there's some recent exciting work in this regard, which is to try and instantiate circuits that are guaranteed to be peaked on average. So in this work, the author showed that if you have random circuits that are just post-selected on this promise being true, namely that they are peaked, they turn out to have all the right properties, namely that they have large circuit complexity in the sense that you cannot compress them down too much. Also, you can show that computing their output probabilities is sharply hard. And there's this other recent work which actually tried to do an experiment, and they had some heuristics for coming up with peaked circuits, which looks like what I described earlier, which is you compose U and U dagger in some places, and then you try to obfuscate that structure. And they had some experimental results, and even had a Bitcoin challenge where they came up with some peaked circuits and asked people to, break them in order to steal some Bitcoin from them, which indeed it was broken in this recent work. But as far as I understand, they withdrew the challenge when this became known. But yeah, so there's a lot of interesting, exciting work in this regard.
Sorry, but if you have to post-select, isn't that very hard?
Yes, that's right. Yeah, so that's not a viable way of producing peak circuits. Okay, so in our work, we use some ideas from error correction to come up with circuits that are conditionally peaked, which I'll talk about what exactly that means soon. But first I'll talk about just a primer on error correction. Okay. So yeah, let's just take the very simple bit flip code or the repetition code. So this has code words 0, 0, 0 and 1, 1, 1, meaning that I take a logical 0 to be represented by 0, 0, 0 and a logical 1 to be represented by 1, 1, 1. So the first stage is to take my logical information from the input and copy it down here to produce the code word. And so this just prepares the 1, 1, 1 state. And then next, let's say there's some error that was applied to one of the qubits. Let's say it's the first one here. Normally, in like a quantum error correction experiment, I would not want to disturb the state, but instead just infer what happened to it. And so you would make these parity measurements. And the idea is that from these parity measurements, you can just learn that there was an X error applied to the first qubit. Okay. Yeah, so because an error here would correspond to an error in the parity on both of these. Right. And next, you would typically use this information to apply a correction. But here in this talk, we are taking a sort of more destructive view of error correction. And what we want to do is just prepare a code state and measure everything. So let's say in this case, there are 3 measurement outcomes, Z1, Z2, and Z3. Now, the way to get back what happened is to perform this unencoding step, which is basically the same as what I mentioned earlier. So you are, after you get the measurement results, you are then applying this matrix that effectively does some bitwise XOR computations. So here I'm just computing Z1 plus Z2 and Z1 plus Z3. And what that tells me, so the first outcome here is the answer of what the initial logical information was, together with what the error that was applied, while the other 2 bits are the syndrome bits. So these are all additions mod 2, and in general, you would just have a large matrix T that just depends on what the encoding circuit is.
Sorry, could you please say again what the error is in this case?
So it depends on what you measure at the syndromes, like at this outcome here.
But I mean, do you like randomly apply X operators to a bunch of qubits?
No. So in this example, there was an X error on the first qubit. And since the logical was a 1, in here I would see like a logical Z1 equals 1.
Sure. Does this depend on working with the classical code?
Yeah, right now this is all classical.
Okay.
Okay. The main thing to note is that once I tell you what the errors were, then condition on that information, you know what the logical register should be in. I guess you also know in this case what the input logical state was. So essentially, you have the logical register peaked on a particular outcome, condition on the syndrome register being in some state. And the idea is that now let's just consider a more general code. And if the error is such that we are below threshold and we have large distance, then we can correct a large number of errors. And the syndrome distribution can also have large entropy. So yeah, the question is whether we can design a quantum advantage protocol based on this. So let's get to the scheme. Let's say we have Alice and Bob. And the idea is just that Alice samples some random code and a particular coherent error channel and gives its description to Bob. And Bob is expected to just prepare a particular code state, apply that error and measure in some output basis and send the samples back to Alice. Okay, and within this setup, you can show that you can have particular codes and error channels such that if Bob follows the protocol honestly, then Bob's output is classically hard to simulate. So let's assume for a moment that Bob really does follow the protocol. Then in the worst case, you can just take some particular binary linear code, and you can show that if you could exactly simulate Bob's output distribution, then bad things would happen in complexity theory. Okay, but now the question is, how do you verify whether Bob is indeed really being honest? So here's like the basic attempt that you can do. So Alice just checks that Bob's outputs are conditionally peaked in the correct place. So what Alice does is, so there's some output, a subset of the output that's syndromes, and Alice just decodes them and verifies that the logicals are correct.
Quick clarification. I must have missed what this looks like a fixed circuit. What is it you're varying to choose the distribution of circuits here?
So the encoding step here depends on the choice of the code. So yeah, we are considering like a family of codes, and the encoding circuit would depend on what the parametric matrices of the code are.
How many elements are in that family? It's an exponentially large space.
Yeah, it can be exponentially large.
And do you mean your error model is always single qubit phase rotation?
That's right, yeah. So there are errors by design. Maybe if you did them on a real quantum computer, you would also have additional errors that you didn't, want them stuck in. But yeah, this is the intended protocol. Yeah, so this has a problem, which is that if Alice just describes what the code is and what the encoding circuit is, then one needn't even have a quantum computer to come up with samples that pass this test, because Bob can just use knowledge of the code and to figure out like random syndromes and logicals that are consistent with those syndromes and just output that. So in the case where Bob is really sneaky, we cannot catch him using this sort of test. So we need to update the protocol. And we also want to reflect the fact that there's some property about the particular error channel that Alice intended Bob to apply. And one way to do this is to use CSS codes. So this will define a pair of codes, CX and CZ. And the nice thing is that you use one code, namely the CZ code, to define what the circuit is. And you use the other code to verify the peaks. And so in particular, if Alice asks Bob to prepare this state, which is the superposition over all CZ code words, then Bob can do so. And it turns out that the state preparation circuit for this state, which is just the logical plus state of the code, does not depend at all on the CX code. So Alice can just keep CX secret for herself and only use it later during verification. So Alice's modified test would be as follows. One is the same peak verification that I outlined earlier, where Alice just accepts if the decoded syndromes are correct. And the other part is to also verify that the syndrome distribution is now correct. And this is kind of our intuition, which is that because of these conditional peaks that occur with very high probability, if you pass both of these tests, then you are essentially sampling from a distribution that is close to the ideal one in total variation distance. So informally, we are saying that checking this TVD closeness to the full distribution reduces to checking TVD closeness of the syndrome distribution. And namely that it is hard for the same set of samples to pass both these tests. Okay, so now that we have reduced to just verifying the syndrome distribution, like we can talk about how hard it is to do that. The problem is that
Sorry, so the only magic states that appear in the circuit are these errors at the end, right? Like these phase rotations, because the encoding circuit will be Clifford.
Yes.
I see. And so I guess that sort of motivates this verifying the distribution part. Because if you didn't have that, then Uber could just classically run the Clifford circuit to prepare the state and then simulate measuring.
Exactly. Yeah.
Okay.
Yeah.
Thanks.
Okay. So the TVD is not sample efficient, but what we can instead do is compute low order marginals of the syndrome distribution, which is sample efficient. And the whole conjecture is that now this test is hard to spoof. So some more details about this low order marginal test. What we do is choose some random low weight parity checks. Sorry about the typo. So it's just a product of X operators, and S is a subset of constant size. And from the samples that Bob sends back, Alice computes the empirical expectation value of these GX operators and also computes them classically, which is possible in this particular setup that we have, and checks if they match. And as a zeroth order check, we can show that this sort of test would distinguish between coherent Z rotations and incoherent errors. And this would give you a quantum advantage protocol that is classically efficiently verifiable if this conjecture that we mentioned earlier holds. Yeah, so that almost brings me to the end, and like what we need are these properties. We want an error correcting code that's decodable classically, efficiently. We want high distance to correct for like a linear number of errors, and possible average case hardness of computing output probabilities. And yeah, I think quantum low density parity check codes are nice and satisfy a lot of these properties. And I think a nice bonus of this scheme is that error correction is exactly what we want quantum hardware manufacturers to focus on the roadmap to building fault-tolerant quantum computers. So it's a nice milestone on the way to them. And yeah, so that brings me to the end, and you kind of see why I said this is sort of efficiently verifiable. So because we only have some tests that verify aspects of the syndrome distribution and not completely checks TVD closeness of the syndrome distribution. Yeah, that's it. Thanks.
Thanks for the nice talk. I'm a little bit out of my league on this, and but your circuit of Cliffords, and then the last row being these rotations, which become T states, reminded me of Bryan's talk earlier,
Right.
which said that if the T states are uniform, or if the T gates are uniform, and at the end of the circuit, it sort of becomes easier to simulate.
Yeah.
So I don't know how to take these two facts and put them together, but maybe you can help
Yeah.
me.
Yeah. So, okay, assuming we didn't open up Bryan's algorithm and like just took the statement at face value, it would not immediately work, because what we want is samples from the output distribution, not just local expectation values. And in fact, when Alice does the test, the low order marginals test, she is computing low order expectation values of certain polys. And so you could use, I guess, Bryan's algorithm for that too. Yeah.
Is there any sort of intuition on why this low order marginal test would be hard to spoof?
So I think on its own, it may not be hard to spoof, but because Alice can compute expectation values, even though Alice also knows more than Bob about what the code is. But yeah, we think that the same set of samples may not pass both the mean value test and the peak verification test.
So could you please say again why it was important to switch from the random classical linear code to the CSS code?
Why it wasn't. So when we just had, say, the peak verification test, and we didn't specify a CSS code, but like just a general other object. Maybe it's some code that's known to everyone publicly. Then it is easy for Bob to just come up with samples that pass peak verification, because Bob knows the code.
Yeah, so why was it important to tell Bob the code? Or is the concern that if it was a classical code, then it could have just in principle been copied by Bob in the past?
Like, you also want to describe the code state preparation, because you want Bob to run something. So you want the circuit to be visible, but not everything about the code to be visible.
And you couldn't like run the code locally and then teleport the output state to Bob, so you didn't have to reveal the code.
We assume Alice is classical.
Okay, right.
Yeah.
Thanks.
Yeah, but if Alice is quantum, then you can just define quantum.
I'll ask you more about that in a moment. Thanks.
Sure.
Okay, last call. Great, let's thank our speaker again. Okay, I believe we have about an hour of a break, and then at 6 p.m. we have the workshop banquet, which is somewhere.
Mara.